Whatever you say.
Okay. Good morning, everybody, and welcome to the meeting of the Review of U.S. Human Spaceflight Committee. We're here in the Carnegie Institute again in Washington, D.C. Thanks for everybody that came out today. We're also being broadcast live on NASA TV, so hello to everybody watching there. And we're streaming live on the internet via the nasa.gov website. So welcome to everybody. Just a couple comments to start off. This meeting is ruled by the Federal Advisory Committee Act. So all comments, presentations, and the discussion today are on the record. We are going to have a public comment period. We plan to start that approximately at 11 o'clock. We'll ask you to come up to the mic. Because of the constrained schedule today, we're only going to be allowed to hear from 5 commenters. So if you would like to speak during the public comment period, there's a sign-up sheet in the back of the room for those 5 people. So go ahead at your leisure and sign up for that. Just if you want to make a comment, we don't have time for you today. Just keep in mind that the committee is available 24/7 via our website, which is http://hsf.nasa.gov. You can give a comment, ask a question, upload a document, and actually we prefer the questions be submitted to the website and that you don't use the public comment period for questions, because we like to get the questions and post the answers for everybody. Please don't interrupt the presentations or the deliberations of the committee members today, and please mute your cell phones. With that, Chairman Norm Augustine.
Thanks, Phil. Good morning, everyone, and thank you for your... Is this working? Can you hear the back all right? Can you hear? Okay, thank you. Very happy to have everyone here. It's always a pleasure to see such interest in the space program. We have been deluged with comments on our website, with emails, with our Twitter, and everything else, and we really appreciate the inputs we've received from the public. I can't emphasize enough how helpful it is to know of the span of feelings that folks share. So welcome to those of you in the room, welcome to those watching on NASA TV. Special welcome to you, Buzz. Thank you for talking to our group previously. And this morning we have I think a very good schedule. A number of people with significant backgrounds in the space program are going to share some thoughts with us. Toward the end of the morning, we're going to have time for the committee to discuss some of the alternative programs that we've been addressing. And I'll give more introduction to that when the time comes, but let me just say that last week we met in Houston, in Huntsville, and at the Cape, and at the end of those meetings, we asked a subgroup of our committee that consisted really of the subgroup leads, the 4 of them plus myself, to meet since last Friday and propose a set of options, and those we will discuss this morning with the idea of adding or subtracting or discussing whatever we care to do with them. As you know, our charge is to provide options to our government. We are not asked to provide a specific recommendation, but we obviously will provide some assessment of the various options for the people who actually make the decision. Our first speaker this morning is a friend who many of us know in the room, who was the President's Science Advisor and the head of the Office of Science and Technology Policy in the prior administration, and had a good deal to do with shaping the space program over the last few years. And I speak, of course, of Jack Marburger. Jack, it's a pleasure to have you with us, and the podium is yours.
Great, thanks, Norm. It's a pleasure to be here and talk about these events that occurred for me 6 years ago when the Chief of Staff, Andy Card at the time, pulled together a group to propose concepts for the long-term future of the U.S. human space exploration program. During that process, the Chief of Staff formed a group we called the Rump Group that consisted of a number of people. I will list their names in a written document that I'll provide to the committee so you have a complete record of that early history. But as a result of recommendations by that group, the Chief of Staff's office formed a set of questions that they sent to agencies, including NASA, Department of Defense, the intelligence community, and some others, whose answers guided the policy from then on. And the process occurred under the normal policy committee, coordinating committee process, PCC process, and the process was augmented by representatives from NASA, particularly, and from the intelligence community. And I sat in on all of those meetings, all of the senior policy meetings in the White House during that period. Out of this process emerged the President's address of January 14th, 2004, and the accompanying policy document called A Renewed Spirit of Discovery. Two features of that process are noteworthy. First, it took place in an unusually rich environment of information. We had numerous reports, studies, commentaries on all aspects of space exploration, reaching back to the 1952 Collier's Magazine series by Werner von Braun, and including work of predecessors of this committee, including a previous Augustine Committee report. Second, the final policy document was a compromise between contrasting policy perspectives offered by NASA and by the White House advisors. In presentations to Congress and to the public, NASA representatives emphasized the NASA point of view, subsequently, which began to appear even during the policy process through leaks to the media. In my own public presentations, and particularly in two speeches I gave in 2006 and 2008 to the annual Robert H. Goddard Memorial Symposium, I emphasized the White House view. NASA decisions following 2004 tended to diverge from the compromise vision toward greater emphasis on a Mars expedition as a primary objective, and minimizing the features of sustainable cumulative capabilities and commercial participation that were important parts of the vision. NASA decision-making did grow increasingly constrained by real budget shortfalls, created in part by the larger than estimated return to flight cost of the shuttle. But it would be a mistake to assume that the actual development path for space exploration since 2004 has accurately reflected the overall concept of the vision. In September 2003, partly in response to the questions to agencies that I mentioned, I drafted my own version of the policy direction then emerging from the deliberations of the Rump Group, and it remains my own personal preference today. And so I would like to continue my presentation by simply reading you that document that I prepared in response to these questions. First question was, what is our vision for future space exploration? Our vision is to understand as far as humanly possible the universe beyond Earth's immediate vicinity, and to use that knowledge to improve the quality of life in every aspect for all people. We will pursue these goals through every means appropriate to the diverse tasks of the enterprise, with respect for the health and safety of those involved, and in balance with other worthy endeavors. Why is it important? Within the Earth's orbit, space exploration has enabled technologies for national security, economic gain, and science. Surveillance, navigation, communication satellites are now part of our military and civilian infrastructure. Scientific satellites looking deep into space and down at Earth are changing profoundly our notion of the substance and structure of the universe and the operation of the Earth environment. These will continue to bring benefits for the foreseeable future. Beyond Earth's orbit, we have sent robotic explorers to every planet in our solar system except Pluto. Each planet and moon visited has yielded new scientific discoveries and challenged our understanding of planetary formation and the possibility of emerging life. Imaginative schemes have been proposed for further enhancing our national security, economic strength, and scientific knowledge using objects and phenomena accessible only from space. Those that require large structures beyond Earth's orbit are impractical today. If such schemes are ever to be realized, the groundwork must be laid far in advance of their implementation. Laying that groundwork is the task of our generation. 3, what contribution does human spaceflight make to this vision? The reference is to the current spaceflight activities. With one exception, it does not contribute in a tangible way to the immediate task of preparing for large-scale development of space resources. That exception is the understanding of the effects of weightlessness on humans. In the future, humans working with robotic systems will probably be required for large-scale development, such as the construction and maintenance of remote facilities, mines, factories, base stations. We do not now, however, possess the knowledge or technical infrastructure necessary to deploy humans safely beyond Earth's immediate neighborhood. Human spaceflight does contribute to society in non-tangible yet compelling ways. It provides lofty goals and promotes human orientation toward acceptance of our place in the universe. Human space exploration has inspired an entire generation of Americans to pursue careers in mathematics, science, and engineering. And U.S. leadership in human spaceflight serves as a highly visible example of how we can apply advanced technology towards peaceful ends. It provides a vehicle for international cooperation and a uniquely positive legacy to future generations. Why is human spaceflight important in the long term? Future desirable large-scale operations in space, such as resource exploitation, climate control, solar energy schemes, will probably exceed the capacity of robotic systems for independent operations. Under these circumstances, human participation can be justified and will likely be required. Until the costs and risks of human participation are better understood and controlled, however, the establishment of goals for such large-scale operations is a futile exercise. The necessary human-oriented studies, which involve placing humans in a weightless environment, can be carried out simultaneously with continued robotic exploration throughout the solar system. Most official studies of human spaceflight conclude that it has value that might be called spiritual or existential. No agreement exists as to what this means, but it is complementary to the value of some kinds of scientific knowledge. We do not study the collisions of galaxies for commercial profit, but understanding such exotic phenomena brings them into the human domain. In the same way, knowing that men and women have visited an exotic world literally humanize those places. Heroic acts and their importance to society are real, and spiritual motivations are among the strongest that we have. Much anecdotal evidence suggests that space exploration provides a vehicle for these social benefits. Programmatic options. Run the gamut from terminating human spaceflight altogether to announcing an Apollo-like sprint to Mars. The options vary in the degree to which humans participate directly, that is, physically, in space exploration. At one extreme, space exploration is entirely robotic. At the other, vast resources are invested to maximize human participation. A balanced approach would prudently build capability for human exploration beyond low Earth orbit while avoiding premature commitment to specific large-scale operations. By careful planning, we can make each step a foundation for a range of next steps, so with time our investments mount, costs and risks diminish, and we keep options open to exploit the right one when we're ready to make a big move. As cost and risk are lowered, the case for human presence in space improves, and the variety of plausible missions increases. We have a vigorous and highly productive program of non-human space operations for science, military, and commercial purposes. The philosophy of going step by step and preparing for the future on a broad front introduces human capabilities only as appropriate, keeping in mind that the ultimate goal is to permit humans to operate routinely on missions where they are needed. The quest to enable all large-scale missions is itself more ambitious than anything yet ventured in space. It includes careful exploration of the moon, for example, and establishment of a base there for in situ resource utilization. This should suffice to capture the public imagination. Our programmatic vision for human spaceflight is to bring the successive spheres of every space frontier within our reach, to diminish the daunting cost and risk of every expedition into this new territory. We can embark upon this mission now because every future mission is encumbered with the same impediments of cost and risk. Reducing risk. Radiation and the effects of low gravity limit the duration for humans to live safely and work in space. The radiation can be simulated here on Earth, but to study weightlessness requires a free-fall laboratory, and we have one, the International Space Station. This is the first existing step, and we aim to build upon it with our international partners. The Earthbound and the space-based work together will provide the data and the ideas that we need. They build stepping stones of knowledge about ourselves that we will need to survive in space. Reducing cost. Some strategies are well known. Miniaturize, improve materials, develop better transport systems, and forge partnerships with robots and with able nations. Other strategies are technically less mature but offer much greater potential payoff. Make heavy parts beyond Earth's deep well of gravity to cut the cost of lifting out to space. And where should we find the raw materials for this? On the moon. This requires a moon base, robotic, and ultimately human crews for oversight. Some consequences of this approach. It optimizes not for a single mission, but for the steady accumulation of technologies and capabilities that provide a base for multiple operations. It emphasizes the role of robotics, of ground-based research, and of system thinking. It places the International Space Station in a larger context. Its purpose is specifically to acquire knowledge that allows us to protect humans in space. This approach is compatible with a reduction of the current human spaceflight program. The current program places humans in space to accomplish missions that with today's robotic technology can be accomplished without them. The result has been to decrease resources available to build the foundation toward future missions for which humans have a more important role to play. We cannot place humans deeper in space for any length of time without solving the problems of risk and cost. The first order of business is to solve these problems, not to use humans in lieu of robots in the safer low Earth orbits. The approach entails extensive robotic exploration of the moon, potentially followed by the construction of a permanent lunar base whose objective is resource exploitation, possibly for economic gain, and to use the material to facilitate further expansion of human exploration deeper into the solar system. This program would be carried out simultaneously with research into the mitigation of human risk factors and the development of new launch and transport technology. Schedule and budget. The pace of advance will be dictated by the level of resources devoted, but a range of budgets permits continued progress. Close cooperation with and even reliance on international partners should be seriously considered. No date should be established for humans to return to the moon or Mars. The rate of advance away from the Earth should be dominated by budget and technical progress, and by no calendar but the winding of the planets along their eternal paths. Well, I wrote that to try to educate and persuade as well as to explain. If I were rewriting this today, I'd add a paragraph on the role and importance of commercial space enterprises and emphasize the importance of sustained effort. And some of that deficiency was remedied in the final version of the policy, but it's been neglected in execution. Let me restate a plea that I made in my 2008 Goddard lecture. If the architecture of the exploration phase is not crafted with sustainability in mind, we will look back on a century or more of huge expenditures with nothing more to show for them than a litter of ritual monuments scattered across the planets and their moons. In my opinion, the all-encompassing scope of the vision we advanced was diminished in the final policy by specific mention of Mars as a target, and the immediate path forward was burdened by deadlines and difficult budget issues. Our view was pragmatic and conservative with respect to human operations, but vast beyond any scenario since von Braun's view, in its view of a future in which the entire solar system is open to the service of humanity. Thank you, Mr. Chairman.
Jack, thank you very much for those comments. And I wonder if we could get a copy of your paper for our committee.
I have a longer version of this that I will, this afternoon.
That'd be terrific, so we could distribute it. We have time for a couple of questions from my colleagues. Does anyone have any questions they'd like to start out with? Please, Chris.
Thanks very much for your remarks. I'd like to ask you to be a bit more specific with respect to your comment on sustainability. Do you view the current architecture, the program of record, as a sustainable architecture, or would you prefer to see that modified in some way?
It's hard to characterize the current program because it has been impacted so much by exigencies and budget constraints. So it's not clear that what's being done is consistent with NASA's intent or with any particular policy intent. So I want to be a little careful about how I say this. Certainly, the sustainability has a lot to do with what society can tolerate and how to carry a vision like this beyond administrations. We have supportive administrations and we have less than supportive administrations. We have recessions, we have booms and busts. And I think it's important to craft a strategy that is not disrupted by those exigencies. And in order to do that, you have to be somewhat careful about establishing firm deadlines and rushing to achieve them. In my view, the most important factor here is sustaining the workforce that has the expertise required to build the various pieces and to continue an initiative over a period of a century. I don't know whether the current mission is sustainable in that sense. My guess is that not sufficient attention has been paid to the sustainability dimension of the program. There's a lot of fixation on how to achieve the short-term goals of the International Space Station. There's a lot of attention fixed on the gap, which in the grand scheme of things is not as significant as we make it to be. So closing the gap as a short-term objective tends to get in the way of the longer-term thinking.
Anyone else? Bo?
Thank you very much for your talk to us. It was very useful. My question is this. If you look into future and consider an undertaking like going to Mars for humans, it's going to be terribly complex, very difficult, and very expensive. And the question is, you didn't say much, how would you envision engaging international or global participation in it, and how would you do it? And would you invite people to be on critical path of this undertaking? Give them an important role where they feel like they are stakeholders.
Of course, the concept of a step-by-step program that establishes infrastructure that can be utilized by subsequent missions. For example, simply putting up communication satellites around the planets that you'd like to visit in the future reduces the cost for those subsequent missions. That's a good example. It will certainly work for Mars. It will work for the Moon. And in a vision like that, there are many things to do. There are many concepts that need to be filled in and parts of the system that different nations can participate in. And while The Europeans, for example, take advantage of communication satellites that we have around Mars. We can take advantage of infrastructure that's left by the Europeans or the Chinese or the Indians or whoever has the capability to put it there. But what we need is a shared vision for what the system has to look like. Power systems, for example, on the moon. Somehow we have to get something up there that can generate power for industrial operations on the moon, which we will need in order to reduce the cost of lift in future missions. So those are things that are not necessarily objectives that a single nation can achieve. All nations should be contributing in a way that is agreed can foster the continued accumulation of capability.
Jack, I had a question that's perhaps almost impossible to answer, but I think you had to do it in your prior job. And you've talked some about the trade-off between human spaceflight and robotics and the balance and so on. How do you deal with the issue of trading, say, the space program against medical research or energy research, environmental research? How did you deal with that?
Philosophically, there is a way to do that, and I mentioned it in one of my Goddard lectures. The point is that in the vision that we advanced, the motivation was not the existential or spiritual motivation for human achievement. Motivation was national security, commerce, science. Not just putting somebody up there on a remote planet. Well, those are missions that can also be achieved by investments in other activities. And so you can weigh the impact of those investments. Now, the impact of space exploration, particularly human space exploration, is very long term. But at least you can get some sense of the domains of human enterprise that might be advantaged by it. Even the objective of encouraging young people to become scientists and engineers and so forth can be achieved in other ways. So I think once you get back off a little bit from this notion that we must, as human beings, just be out there, then which is not, you can't compare that with anything, any other expenditure, so it's not possible. Once you back away from that, you get into spheres where you can compare. What's the advantage of having $30 billion invested in NIH, for example, versus investing $5 billion in an enhancement to a step-by-step program?
Yeah, Chris?
This is just to follow up on this this very interesting discussion. How would you factor into that sort of scheme the in a way that would be comparable, the advantages of, saying, conducting fundamental research in cosmology?
Well, the fundamental research in cosmology is in a different category. That's in the category of, we are human beings, we live in the universe, we must know about it. There is an urge to do that. And there are some questions that are intrinsically very interesting. Whether or not intelligent life exists elsewhere in the universe is an extremely interesting thing that humans ought to be interested in and willing to spend something on. The origin of the universe is sort of an intrinsically deep and interesting question that humans have spent a lot of brain power on for a long time. And similar things, the ultimate structure of matter. We're spending billions of dollars on particle accelerators to determine the structure of matter, which has essentially no impact other than its spin-offs on human on enterprise, commercial enterprises and human health and so forth. But it's an intrinsically interesting question. So it's hard to say. In my view, those kinds of questions are more intrinsically interesting than the issue of having a human being on a remote planet, which doesn't, you don't get too much out of that except for the pride of knowing that human beings can do that. And whereas the knowledge that you get from studying cosmology and so forth is a permanent knowledge. Many people can share in the enterprise of getting it and thinking about what it means and so forth. Whereas I view the flags and footsteps model as having less impact in the long term.
Jack, thank you very much for sharing your thoughts with us. We appreciate it. It's great to see you again.
My pleasure. Thank you.
Take care. Our next speaker this morning is representing the Mars Society, well known to many in the room, and that's Bob Zubrin. Bob, welcome.
Phil, are we going to be able to project my charts? Or oh, there we are. Okay, thanks. Mr. Augustine, members of the committee, I'd like to thank you for inviting me here to express my views and insights and those of the Mars Society on where the American space program should be going, and to thank you for coming out of your private pursuits to do this activity, because I think this is a very important activity that you're engaged in here. I hope you'll forgive me if I just take a few seconds to present my credentials, since some people here might not be familiar with me. I'm an engineer with a master's in aeronautics and astronautics and a doctorate in nuclear engineering. I have over 2 decades of aerospace industry experience, including 7 years at Martin Marietta, Denver, and Lockheed Martin, doing preliminary design of interplanetary missions. And I also, for a number of years, have run my own company, Pioneer Astronautics, which has done around successfully about 40 NASA contracts of various sorts. Written over 200 publications, including 9 patents and 8 books, 5 of which are in this field. And I also lead the Mars Society, international organization of people committing to furthering the exploration of Mars, which has done various things, the most notable of which has been to establish a simulated human Mars exploration station in the high Arctic on Devon Island, in the polar desert, 900 miles from the North Pole. Okay. My remarks today are going to cover a number of areas. First of all, why NASA needs a definitive goal with a definitive schedule. What that goal needs to be, and how it can be accomplished in that kind of way. So, to begin, in recent years, and in fact, it's now rolling into decades, people have been concerned, politicians, congressmen, journalists, why are we stuck in Earth orbit? Why have we not gone anywhere since the conclusion of the Apollo program? And it's a very valid concern, and it needs to be addressed. And I think it can be addressed if you look at how NASA has actually operated over its history. It's operated in 2 fundamentally different modes of operation, one of which is that which prevailed in the Apollo era from 61 to about 73, and I call that the Apollo mode. And the other, which has prevailed since, which therefore I call the shuttle era mode, or shuttle mode for shorthand. Okay? Now, there's 2 completely different styles of operation that were engaged in these 2 periods. In the Apollo mode, what's done is national leadership sets a definitive goal with a definitive schedule. NASA is assigned to figure out how to do it on that schedule. A mission is designed. Components are designed to fulfill that mission. They are built, and the mission is flown. 1, 2, 3, by the numbers. That's how we got to the moon. In the shuttle mode, on the other hand, okay, what happens is programs are proposed by various constituencies, whether constituencies in the technical community, from various NASA centers, from various states or other interests, and some of these make it through the political system, and we get an assortment of technical programs undertaken which are not really coordinated with each other, and which are subsequently justified by a rationale which is produced to be able to claim that these programs would be useful at some point in the future when someone actually had a mission to go somewhere. Okay. If you want to use a metaphor to compare these 2 modes of operation, think of 2 couples, each of which would like to have their dream house. Couple A talk about their dream house, and then they hire an architect to design the dream house, and they get the drawing done, and then they go to a contractor, they build the house, and they have their house. Couple B goes out every weekend and cruises garage sales and sees items that they think might be of interest at some point in the future when they want to build a house. So they pick up a spiral staircase, some Doric columns, aluminum siding, whatever, and they pile it up in the backyard. And then every once in a while when the in-laws come to visit and pa-in-law says, "Why do you have all this junk piled in your backyard?" They say, "Well, it's to build a house." And he says, "Well, I'd like to see the plans of this house." So they hire an architect and they tell him, "Look, we want you to design a house and it has to include all of these parts." Okay? So the house is never built, but embarrassment is avoided because a rationale is produced for the various purchases. And so that is the difference of the two modes of operation. And it is apparent which one is going to be more productive, and the numbers show it. If you take NASA's budget from 1961 to 1973 and you add it up in today's dollars, it's around $230 billion. Divide that by 13, it's $18 billion a year, which is the same as NASA's budget this year. That is, during the Apollo period, while there was, like 1966, it was more, and other years it was less, on average, NASA's budget over that period was the same, within a few percent of what it is this year or last year, and frankly, the same in general order of what it's been since 1990. So let's compare what NASA accomplished with that budget between 61 and 73 compared to what it accomplished with the same budget between 1997 and today. Okay? Between 1961 and 1973, NASA built and flew Mercury, Gemini, Apollo, Skylab, Ranger, Surveyor, Mariner. We did all the technology needed to development to do Pioneer, Viking, Voyager. Over 30 lunar and planetary missions in that list. We did technology development of an amazing sort. We developed hydrogen, oxygen rocket engines, multi-stage heavy lift launch vehicles, in-space life support, space suits, deep space navigation techniques, deep space communication techniques, space rendezvous techniques, lunar landing techniques, re-entry techniques, nuclear rocket engines, space nuclear reactors, radioisotope thermoelectric generators. The list goes on. The entire bag of tricks that we use to do everything that we do in space was developed. And we developed the Deep Space Tracking Network, and we built Cape Canaveral and Johnson Space Center and Jet Propulsion Lab, the works. And we inspired a generation of youth to want to enter science, a point that I'll get to again later. That by comparison, with the same budget, between 1997 and 2009, NASA flew 47 shuttle missions, which allowed them to repair and upgrade the Hubble Space Telescope and partially build a space station. And we flew about a dozen lunar and planetary probes, and we did no significant technology development to speak of. So comparing these two records of accomplishment over identical periods with identical budgets, it is difficult to come to any other conclusion that the degree of accomplishment that one can get using the Apollo mode of operation is at least in order of magnitude more effective than can be done with the shuttle mode of let's just work on technologies and do projects that are interesting and potentially valuable, and someday we'll have the set of tools we need to go, as Mr. O'Keefe put it, anywhere, anytime. Okay. The first program works, the second essentially does not. So, in short, we really need to take stock. This idea of having an unfocused program is simply unworkable if you want to have an efficient program. We need to take stock, decide what our goals really are, and allocate our priorities in accord with those goals. Okay. Should we continue flying the shuttle? Well, if our goal is to continue ferrying people up and down to Earth orbit, as this is what we think our primary activity in space should be, then that is worth considering. But if our goal is, in fact, to send humans to the moon or Mars or wherever beyond low Earth orbit, then we have to allocate our priorities and allocate our funds to support those objectives if we wish to accomplish them. And we have to set a definitive schedule to achieve those objectives. Okay? The Apollo mode got us to the moon. It could get us to Mars if we choose. The shuttle mode will never get us anywhere. What's needed, though, to set a goal, set a schedule, and accomplish the project is leadership. In the beginning was the Word. Now, what should the goal be? In my view, the goal needs to be humans to Mars within a decade. Okay. Why Mars? Okay. Because of all planetary destinations within reach, Mars is by far the most important, offers the most, both scientifically, in terms of social benefits for our nation of if we do accept this challenge, and in terms of what it portends for the future. In terms of science, okay, Mars is the Rosetta Stone for letting us know the truth about the prevalence and potential diversity of life in the universe. Okay. We now know that Mars had liquid water on its surface, including standing bodies of water of various kinds, for a period on the order of 1 billion years, which is 5 times as long as it took life to appear on Earth after there was liquid water here. So if the theory is correct that life is a natural development from chemistry through chemical complexification, wherever you have an aqueous environment and reasonable temperatures and an assortment of various minerals and so forth present, then life should have appeared on Earth, on Mars, as it did on Earth. And if we can go to Mars and find fossils of past life on the surface, then we will have proven this conjecture, and we will know that life is a general phenomenon. And since we now know that planets around stars are a general phenomenon, we've detected over 200 extrasolar planetary systems. It now appears that planets around other stars are more the rule than the exception. Since every star has an appropriate distance, near or far, depending upon the brightness of the star, where you have acceptable temperatures for liquid water, if life develops with reasonable probability wherever it has planets within this range, then life is everywhere. We're living in an inhabited universe. This is worth finding out. Okay? Furthermore, if we can send astronauts to Mars and drill down into the subsurface where there is almost certainly liquid water underground on Mars, okay, we know that because we've now seen a runoff, a transient runoff of water occurred during the lifetime of MGS from the side of a crater, which means there had to be a reservoir there. We're seeing methane vents coming out from Mars, which means at a minimum there has to be hydrothermal activity underground on Mars. Okay? If we can drill and reach that groundwater and bring it up and see if there is life in the water, because if there is life living on Mars today, that's where it is to be found, in liquid water. Okay? And we could examine that life. We could find out if it has the same chemical structure. All life on Earth has the same biochemistry, all these RNA and DNA and the amino acids of the same group. And does life on Mars replicate that pattern? In other words, is life on Earth the pattern for all life everywhere? Or are we just one particular example drawn from a much vaster tapestry of possibilities? This is worth finding out. This is something that thinking men and women have wondered about for thousands of years. There is no comparable science to be done on the moon. Okay? You can go to the moon, you can date the craters, and you'll know that Aristarchus is this old, and this is when this meteor landed, and that is when that meteor landed, and somebody can get a paper published in the Journal of Geophysical Research out of that, but that is not something that changes humanity's worldview. This does. Okay? So Mars is vastly more important scientifically than the moon or other alternative destinations that are actually within reach of the human spaceflight program. Secondly, the challenge. I believe that civilizations are like individuals. We thrive when we're challenged. We stagnate when we are not. And a Humans to Mars program would be a tremendous bracing challenge for our society, and particularly for our youth. Okay? It would say to every young person in this country, learn your science and you can be part of pioneering new worlds. And out of that challenge, we would get millions of scientists, engineers, inventors, technological entrepreneurs, medical researchers, doctors, people who add to our military strength, our industrial strength, our social progress, advance our society in every capacity. And and this is really worth adding emphasis to. You know, the Apollo program doubled the number of science graduates in this country at every level, high school, college, PhD. And we're still benefiting from that today, okay? Because, you know, these 40-something technological entrepreneurs who built Silicon Valley in the 1990s, these were the 12-year-old little boy scientists of the 1960s who got into science because they were mad for space, because of what was going on. And now in this day and age, a Humans to Mars program would have an even greater social impact because the science and engineering professions are open to women today in a way that was simply not the case in the 1960s. So in addition to millions of little boy scientists, we're getting millions of little girl scientists. And these people would be making their contributions that add to our economic progress, our medical progress, our military strength for decades to come in a way that totally dwarfs the expenditure. But you have to challenge them. You're not going to challenge the youth of today with the idea of replicating the technological feats of their grandparents' generation. Okay? Youth loves adventure. We invite them to adventure. We raise their morale. We can address this problem. And then finally, there is the issue of the future. Okay? Mars has the resources to support life. Therefore, it also has the resources to potentially support civilization in a way that the moon simply does not. Mars has liquid water on it. We've now imaged places on Mars, continent-sized regions that are 60% water by weight in the soil. That compares to the moon, where people are talking about parts per million or maybe higher concentrations at 40 Kelvin and shadowed poles. There's carbon on Mars. There's virtually no carbon on the moon. We're a carbon-based life form. Everything we eat, everything we wear, whether it's natural or synthetic fibers, is made from carbon. Okay, this is made from carbon. Our fuels are made from carbon. We need carbon. We have nitrogen on Mars. It's the minority constituent of the Martian atmosphere. Okay, nitrogen's absent on the moon. Another element fundamental for life. And Mars has had a complex geologic history that has created mineral ore that can concentrate geochemically rare elements. You know, human beings have used copper since Egyptian times, but copper is actually a very rare element on Earth in terms of percent of the crust. It is, though, accessible because there are geological processes that concentrate it. The moon has not had these sorts of geological processes. Mars had, and that makes available ore. It also has a 24-hour day, which is what is appropriate for growing plants in greenhouses. It has an atmosphere which is thick enough to basically mask out solar flare, so it can use thin-walled greenhouses on Mars instead of thick-walled greenhouses, which is what would be needed on the moon, assuming you had plants that could accept the 2-week light-dark cycle. So you can do agriculture on the Mars in a way that's simply not possible on the moon. So one could go on, but in short, for the coming age of exploration, Mars compares to the moon as North America compared to Greenland in the previous age of exploration. Greenland was closer to Europe. Europeans reached it first, but it was ultimately too barren an environment in which a new branch of human civilization could be established. In contrast, North America is one in which one could be established and flourish. So if we're talking about going into space to stay, if we're talking about sustainability, you want to go to where the resources are, okay? The contrast that is sometimes drawn between Mars as the flag and footprints place and Moon as the place where you go to stay is exactly the reverse, okay? A moon base would have much greater logistic requirements than a Mars base because on Mars, you don't have to ship your water to Mars. The water is there. The carbon is there. It's all there. And if we can make use of the resources, we can establish ourselves there. And if we can establish ourselves there, if we, in our time, can do what we can do, which is establish that first little tiny human foothold on Mars, then we'll put our stamp on the future because hundreds of years from now, there will be human civilization on Mars. And when they look back at this time, there'll be nothing that anyone is doing in this period in history that they will consider more significant than what we did to make them possible. Okay? You know, 1492, you ask any American what happened in 1492, they'll say Christopher Columbus set sail. But in 1492, England and France signed a peace treaty. The Borgias took over the papacy. Lorenzo de' Medici died. To people into current events, those might have seemed more important, but to us today, it's Columbus's voyage that stands as the important event. Similarly, this. Now, I said humans to Mars in a decade. How is that possible? Okay, I mean, various mission architectures that you've seen undoubtedly make it seem like a very futuristic proposition, but it is not. Okay, and now I'm going to walk you through how this can actually be done in brief. Unfortunately, not in as much detail as I'd like, but I've written a book on the subject, and the details are all there. May we have the next chart? Okay, first of all, how long does it take to get to Mars? It's the same question as how much rope does it take to connect two posts that are 10 meters apart. In principle, it can take any amount, okay? But it can be done with 10 meters if you pull it tight. And the thing that pulls it tight is the schedule, okay? The thing that made Apollo work was the schedule. Okay? Kennedy said we had to be on the moon by the end of the decade. Had he not done that, the program would have failed because there were any number of factions with all sorts of other projects that they would like to do, space stations, Saturn IXs, nuclear rockets, who were willing to say, well, you can't do your program until you do my program. But at a certain point, they were squeezed out of the picture when the rope was pulled tight because people finally said, look, do we really want to go to the moon or don't we? And that's how this happened. Okay, but the issue is whether you want to collect the posts or whether you want to sell rope. So let's look at a couple of rope sales. Next chart. Okay, of course, there's the lunar base, the lunar toll booth. Okay, the previous administration, in announcing the vision, President Bush said, we got to go to the moon because you can launch from the moon easier from the Earth, and indeed you can. But before you launch a spacecraft from the moon, you have to get to the moon, and the delta V required to go from low Earth orbit to the lunar surface is actually greater than that to go from low Earth orbit to the surface of Mars. So even if there was a lunar Cape Canaveral in place right now, and they were making propellant and giving it away for free to anyone who would stop by, it still would not make any sense to go to the moon. Okay, the next chart. Okay, then there's this one. Okay, there's the Advanced Propulsion Crowd. You have to build our giant spaceship. Here's one that was designed under the Prometheus program. You can see it's quite large. Mars is there for scale. And they had all kinds of fantastical assumptions about it, but in fact, A, it isn't necessary to go to Mars, and B, if you actually do the mission analysis using real numbers, you find out it offered no mission advantages at all. Next chart. Now, this is one we commonly hear today, that you can train for Mars on the moon. And certainly you can train for Mars on the moon, but you can do it in the Arctic at 3 orders of magnitude lower cost. And this, by the way, is a photograph of the Mars Society's base on Devon Island on the rim of a 20-kilometer diameter impact crater in the middle of a polar desert. And we just had a 1-month mission there. It cost us $75,000. If you want to do it at higher fidelity, you could up the budget an order of magnitude, and it would be $750,000. It would still be a trivial percentage of the cost of doing practice exercises on the moon, and we can initiate such activities today, not waiting until 2019 or something like that. Okay, so that justification isn't there. That leaves the question, how do we actually do a human Mars mission? Next chart. Okay, well, any mission requires an appropriate launch vehicle. And by the way, I'm showing you charts now that were actually developed when we designed this mission, which is known as the Mars Direct Plan, which was designed at Martin Marietta back in 1990. And as you know, Mr. Augustine, one of the great benefits of working at the Martin Company is when you leave, they let you keep your charts. So here, this is a heavy lift vehicle, in this case shuttle-derived, 4 SSMEs, 2 solids, ET core, and a hydrogen-oxygen upper stage. And I hope I won't disappoint you too much if I don't give you an extended pitch on why this launch vehicle is better than various other launch vehicles that have been shown to you, like the Ares 5 or the Direct vehicle. Frankly, any of them will work. Any heavy lift launch vehicle with an upper stage to do a large-scale injection on Trans-Mars will suffice. What won't work, however, is not having a heavy lift launch vehicle. And this is a subject that, I think is very much before you right now. Some people want to abandon the goal of heavy lift. If you, look, we cut the contract on the Saturn V in 1962. We flew it in 1966. We were on the moon 3 years later. If we had a heavy lift launch vehicle today, we could be on the moon within 4 years easily. And the reason why we haven't gone anywhere since the mid-'70s in space is primarily due to the fact that we haven't had a heavy lift. Okay, any number of people, including me, have designed various plans or attempted to go to the moon or asteroids or Mars or wherever with multiple launches of medium lift launch vehicles, and the plan always completely breaks down because you have to launch 4 or 6 or whatever medium lift vehicles, not only successfully but on schedule, and you get ridiculously low mission reliability figures, and the plan becomes unacceptable. But if we have heavy lift, we can do this. And that's what this does. This vehicle, as designed, could lift 120 tons to LEO, but more importantly, using that hydrogen-oxygen injection stage, it could throw 47 tons on a direct trajectory to Mars or 59 to the Moon. And that's how we want to do the mission. Just lift and throw and let it go. Send the payload to the planet with the same upper stage of the same booster that lifted it to orbit in the first place. That's how we've done every real unmanned planetary mission. That's how we did the Apollo lunar mission. If you can do the Mars mission that way, right there you've gone 90% of the way towards taking the Mars mission out of the world of Battlestar Galactica fantasy and putting it in our world. So what do? Next chart. Okay, this shows a mission sequence. In the first year of operation, you launch one of these boosters off the Cape, use that upper stage to throw a 40-ton payload on a minimum energy trajectory to Mars. What is that payload? Next chart. Consists of a number of things. The primary object is the Earth Return Vehicle, or ERV. Okay, this is a little rocket ship for coming back from Mars to Earth. It's got a small cabin that can house 4 astronauts on a 6-month transit from Mars to Earth. No one's in it now. Then below that are 2 methane-oxygen chemical propulsion stages, which, however, are unfueled. And then slung below the vehicle, not shown in this diagram, is a light truck, which in the back of it has a nuclear reactor, 100 kilowatt power. Okay, this thing flies to Mars, use the aerobrake to capture into Mars orbit. After we see the weather's okay, we bring it in, use the aeroshell to plow us down to subsonic speeds, pop a chute, come down soft with rockets, just like we did in Viking. Okay, so now you got this thing on the ground. Then you telerobotically drive the truck a couple of 100 yards away, deploy the reactor on the ground, turn it on. Next chart.
I hate to hurry you here, but we're getting close to time.
Okay.
This is very interesting, but we need to move on.
All right. Using very elementary chemistry, you make the propellant, okay? And this has all been demonstrated in full on Earth, actually, since the gaslight era. Next chart. Skip it. Next chart. Okay. Then at the next launch opportunity, you launch 2 more boosters off the Cape. One shoots out another Earth return vehicle. The other shoots out a HAB module with 4 astronauts in it. Next chart. Well, that shows the HAB module. Next chart. Okay, it's a basic tuna can HAB with a number of rooms and a solar flare storm shelter in the middle, which you can shield with provisions. You don't need extra mass to provide shielding. Next chart. Okay, we'll skip this. Next chart. Okay, we can make artificial gravity on the way to Mars, and this is very important so the crew's health doesn't deteriorate, and it also means that we don't need to do another 30 years of research on the space station on zero-gravity health effects on the crew because we can avoid them through simple engineering. Next chart. Next chart. Keep going. So this is a concept of the base. You land in the immediate vicinity of the Earth return vehicle. If you land some distance away, you have a ground rover that can get you to the Earth return vehicle. You also have a backup Earth return vehicle that you can direct to the site if you do not land accurately enough to drive there. You're on the surface for a year and a half, which allows you to do substantial exploration over a period of time. At the end of that time, you get in the Earth return vehicle, you take off, you fly back to Earth. You leave your HAB on the base, so on the surface, so each time you do this, you add another HAB to the Martian surface. There is nothing in this that is fundamentally beyond our technology. Let's move forward quickly through a couple of charts. Keep going, keep going, keep going, keep going, keep going. There. Okay. Now, the moon, if you also develop lunar landing stages, you could use the same set of hardware to land on the moon, and that could be done as a tangential goal of the program. I would not recommend the moon as a precursor mission for a Mars because you do have to develop lunar landing and ascent modules, which are not utilizable by the Mars mission. However, you could do a near-Earth asteroid mission as a precursor because a near-Earth asteroid mission can be done with a subset of the Mars hardware. In other words, I'm not proposing a near-Earth asteroid program. I'm proposing that you set your goal on Mars, and in the course of doing that, there are certain other activities where you exercise a subset of the Mars hardware, which gives you greater confidence and have a certain value in themselves. And a near-Earth asteroid mission could fall into this class. So there it is. The technology is there, okay, to do this. Going to Mars on an absolute scale is more difficult than going to the moon, but relative to our technology today, this is a lower order of challenge. In 1961, we didn't even know if people could eat in space, okay? And we got to the moon 8 years later. The amount of technology we have to develop to accomplish this plan is modest compared to what had to be developed to do Apollo. And for us to say today that this is beyond us, that is this beyond our capacity, our skill, or our courage, is saying that we have become less than the people that got us here, and that therefore we are going to give less to the people who will follow in our footsteps. And I would say that that is something that this country cannot afford. So we're here. I think this is potentially a great moment. It's a great moment because it's a moment in which great things are possible. You've got a new administration which is re-examining everything, an administration which is committed to audacity and hope and the fierce urgency of now, okay? Well, and which has sufficient political support in Congress to actually implement a bold program should they decide to embrace it. The American people want and deserve a space program that is really going somewhere. By taking decisive action, by making a decisive recommendation to break us out of this stagnation that we've had in the space program for several decades, for 4 decades. 4 decades of stagnation is enough. Mr. Augustine, members of the Commission, I'm asking you to make a bold recommendation to Mr. Obama that he seize the time and move America forward in space. Thank you.
Well, thank you very much. Your enthusiasm is certainly not lacking, and we appreciate that and admire it. I'm afraid our time is used up, so we won't be able to ask any questions, but we'll read your book.
All right.
Thanks for joining us.
Thank you.
We now are going to turn to the issue of performing science related to the human exploration program, and certainly its interaction with robotic programs. We're going to hear 4 briefings on this, different aspects of sciences. The first will concern the biological and physical sciences, and our briefer will be Elizabeth Cantwell. Thank you very much for joining us.
Good morning. Thank you very much for having me. It's a bit daunting to go after Bob Zubrin. I cannot bring the level of zest that he does to the table, so I just ratchet down a little bit. But I always appreciate when you speak. I've seen you many times, Bob. As Mr. Augustine said, my name is Betsy Cantwell. Several of you on the committee have some familiarity with me. I welcome this chance to discuss my experiences and perspectives on life and physical sciences in low-gravity environments. I've been a researcher for many years in this area, a research manager, and perhaps for an even longer time, a critiquer in the form of many National Academy reports in this area. I'm currently the co-chair of the National Academy of Sciences Decadal Study on this subject. My co-chair is Wendy Court from the University of Colorado. And as this study has just kicked off, I will not have a lot to report on our findings. I will have a couple of slides where I discuss our approach, but I do have a long career and a long association with this research area, and I'll use my own background and discussions with colleagues to give you what I hope is a useful perspective. Next slide, please. This is very much in my face. A decadal study typically develops a set of priority research topics for NASA and options for implementation plans for future missions. NASA has commissioned decadal studies. Now I have to have it in my face. I didn't like that, but I'll do it. NASA's commissioned decadal studies a number of times over the year, and you'll hear from my colleagues after me. This is somewhat unusual. It was requested by Congress to focus on a greater understanding of life and physical sciences phenomena in reduced gravity environments. The objectives are fairly common for a decadal study, but let me point out that NASA has asked the National Academy to focus on research areas that enable exploration missions and are enabled by exploration missions. And as a committee, we've assiduously tried to keep our focus on the future and the value that a research portfolio in these areas can bring. I will discuss this research portfolio in the context of both enabled and enabling, but I'm going to focus on enabling. You'll see that they're hardly mutually exclusive. On the bottom of this chart, let me just point out there's a little graphic that outlines the connection between life and physical sciences in low-gravity environments, which is both some commonality and relevant phenomenology, and I'll give you a little bit of a discussion about that, and exploration requirements. I'll also discuss that. And the steering committee for this decadal study has discussed the commonality elements between enabled and enabling. And you'll see as I talk that there are a number of commonalities. There's obvious links between the two, but the key link that I'd ask you to pay attention to is the need for common infrastructure. for research laboratories in low and microgravity environments. I understand there's been a great deal of discussion so far in both public and private committee meetings regarding the ISS. I have a place at the end of this talk for a little bit of a discussion about that. Next slide, please. My last slide on our decadal study, let me tell you about the 7 subcommittees that we're in the process of populating with experts. They will cover the basic areas of expertise most relevant to life and physical sciences in reduced gravity environments. The country has some history in this area. We also have a strong sense of the need to address translational research as systems elements of both human spacefarers and spacefaring hardware are such an important potential endpoint for research in this area. The bottom line is that there's an incredibly broad suite of research areas bound tightly by infrastructure and systems applications. Next slide, please. Let me start with a short discussion that can be of science that can be enabled by access to reduced gravity environments. I'd like to point out as I begin that there's a history of research programs in all of these areas that I'll discuss today. Most of the research that in these areas that might have focused on reduced gravity environments over the last decade has been reduced in cost by about an order of magnitude or in budget. I'm not actually going to discuss that. I'm happy to answer questions, but I'd like to point out that we've had at various times in the history of this country various sizes of research programs in this area. It's down around $50 million at the moment. I'd be happy to field other questions, as I said later. In the life sciences, studies in things like mechanobiology, topics like cellular mechanotransduction, these are areas where the absence of the ubiquitous terrestrial mechanism of gravity will often yield new results. Similarly, gravitational effects, gravity affects behavior such as gravitropism, and this is something that can be uniquely studied in a low gravity environment. I'd like to point out that as we have reduced our funding and studies in this area, both the Europeans and the Japanese, the international community in this area is very robust at the moment. Also in physical sciences, there's a number of areas where gravity, while not inducing an effect, can mask it substantially in a terrestrial environment. So investigations in phase transitions, for instance, are uniquely able to produce new results in a low gravity environment. And in combustion physics, looking at surface reactions or soot dynamics, in the absence of convection, can and has elucidated mechanisms that have not been seen in and are very difficult to see in a terrestrial environment. Next slide, please. As a start to research that enables exploration, I'm showing you here some elements of human and exploration systems that are relevant for life in physical sciences. There are risks, and I've outlined some risks here, and I've shown you mostly risks for humans. There are also clearly risks for hardware systems. There are also system functions. There are a host of requirements associated with expanding our abilities to explore in space. And there are numerous gravity-dependent phenomena that are imperfectly understood and play a role in all of these areas. Next slide, please. This is a busy slide, and I'm not going to cover every word, but I wanted to give you a sense of where scientific investigations can, and in many cases must, play a role in some of the challenges associated with human exploration. What you see here is a graphic of 2 of the exploration scenarios, and there are many more. I know you all are well aware of all of them, with a representation of the elements of exploration challenges that can be addressed with research in life and physical sciences, research in low gravity. You'll notice that there are competencies such as radiation, various elements of materials development or materials understanding, and multi-phase flow that show up all over the place. There are a number of key research areas that must make a contribution across the board to solving these challenges. Next slide, please. Okay, this slide is a very small selection of areas from across this research portfolio where there are links to terrestrial challenges. I show you this not because I'm interested in demonstrating dual use. My intention is to show that the plethora of science commonalities across exploration and terrestrial challenges do exist. There are absolute science commonalities. Translation of these scientific endeavors to meet either an exploration challenge or a terrestrial challenge would represent an entirely different set of considerations. In other words, it takes a different set of considerations to translate a science endeavor to a terrestrial challenge, such as meeting our current energy portfolio needs, or an exploration challenge, such as aerospace energy or power. Next slide, please. Onto research platforms. All of these modalities that you see here, which is everything from drop towers, where you can get about 10 seconds of low gravity, to the ISS, or something that doesn't exist today, planetary laboratories, where there's a continuous access to the reduced gravity environment that we'd be interested in, are useful. But it is ISS and something like a planetary laboratory concept that hold the most promise of utility because of the continuous availability of a low gravity environment. So let me give you briefly the perspective of my science community on the ISS. Right now, it is the only scientific laboratory we have that makes low gravity continuously available. It's all we've got. Though we have hardly, in my decadal study, begun looking at an integrated analysis of research that we would like to see done, I can tell you that there's a great deal of important work that can be done on ISS. And while we have not produced our results yet, there's a very useful ESA study that's on the street from September 2008, looking at their integrated life and physical sciences portfolio. And I recommend that to you. We, the Europeans and the Japanese, all have emplaced experimental capabilities to do life and physical sciences research on ISS. And we finally have the ability to have 6 crew members on board, which allows us a lot more opportunity to utilize those capabilities. Let me just point out that, at least from the perspective of my science community, in the life sciences, there's a lot that can still be done on ISS to reduce human health risks. Most importantly, bone and muscle. There are immunological studies that are very important to be done, cardiovascular, and of course, looking at the risks of radiation and how to mitigate those. And on the physical sciences, and these are really perhaps focused on fundamental research, but that can directly impact and help almost any exploration future you can predict. Cryogenic fluid mixing, multi-phase flows, which is an incredibly difficult problem, which we do not understand at the levels that we need to understand it, and all kinds of heat transfer issues. And the last slide, please. So this is essentially, the slide is just a distillation of everything I've talked about. I wanted to make sure that I had plenty of time to answer questions if you have them about this portfolio. I apologize for not being able to go in greater detail about the considerations of this particular study, but we have just begun. We have a really remarkable group of people who have signed up, approximately 60 or 70 people who have signed up. I have a 19-person steering committee, and I will tell you that many of them have come to the table once again to provide recommendations because they really believe in doing this kind of work, even though many of them have over the years seen their work funded at lower and lower and lower levels. So thank you.
Thank you very much. We do have time for questions, so Chris, you want to start out?
Thank you. Thanks very much for that presentation. At our last meeting in Cocoa Beach, we talked about a candidate set of figures of merit that we would apply to all the scenarios that the committee's going to consider, and one of those figures of merit is going to be scientific. It's science, value for science. Not that that's necessarily the driver, but it's clearly an important figure of merit. So what I'd like to do is try to, based on your presentation, to try to draw some conclusions within this domain at least for how we might try to scale different scenarios. And it seemed to me, but don't let me put words in your mouth, that's why I'm asking the question, that the most directly relevant comment you made, or maybe the most important comment you made in that respect, was your comment that the International Space Station and planetary laboratory access hold the most utility because of, and planetary laboratories hold the most utility because of continuous access.
Yes.
Would it be right then for us to take from that scenarios which establish, which either keep the ISS flying for some time or establish a long-term lunar base or a Mars base are the most interesting from the point of view of your science because of that continuous access to lower microgravity, and scenarios that don't establish those kind of bases are less favored? Or if that's not right, tell me what's right.
No, that's correct. Certainly, and let's talk about less favored for a moment. You just can't get as much, and we're talking about a science portfolio that is focused on producing results that allow us to make really valid scientific statements. You've got to have continuous access to experimental facilities that give you the time on target so that you can get enough data to make whatever statistical inferences you need to make. Science typically requires access to scientific facilities for not just once, but for enough time, and that can be perhaps in however many shots you get of a large laser, for instance, or continuous access. Either way you look at it, it has to be a lot of time on target. And in this case, that's time in the relevant environment.
I'd like to follow up with a question,
Yes.
if I could. Appreciate the need for time on target, but could you also share your perspective on the relative value of robotic experimentation, as well as, clearly there's a need for human exposure here in order to get the proof in the pudding, but have you made any assessments about what the opportunities might be for robotic excursions that may be valuable?
So certainly as a committee, we have not had that discussion. So any comments that I make are really personal comments. And my personal experience says that there are times when one could envision creating an autonomously operated laboratory. However, my personal experience is that when you really do top quality science in an autonomous manner, it is extremely expensive. And it may not cost less than having a human there to do it. Yes.
Please, Jeff.
I've been getting a lot of correspondence from people suggesting to me that there's a factor that we haven't talked about, which is if you're going to get good scientific utilization of the ISS, it's not just a question of how much mass you get up to and down from it, but a question of how frequently you can do so. That we could do a lot more good science up there if you could discover things and send new things up or bring samples back with greater frequency and time. I'd like to hear your comment on that.
Well, again, personal comment, but that's almost common sense. The question is, how much additional value could we actually bring in the time, whatever that time is, that we have left to utilize station? And I didn't make a very clear comment, but let me say that those kinds of considerations really ought to, for this science, this is an international science community, and it's clear that there's a lot of international capability on the station. Those kinds of discussions should be held with the entire international community.
Please. Leo, Murray.
I just have a quick question about interest in the community. Of course, there are a lot of core of scientists that are very much interested in continuing microgravity or other research in space. But a lot of them have been burned over the years, and you kind of alluded to that. My question is, if access became more regular, perhaps through commercial means, do you think that there would be a resurgence in interest, or would there be wariness in coming back? And particularly in perhaps commercial ventures, like perhaps pharmaceutical companies.
I think well, again, this is a personal comment. I think you'll see both. There are members of the community, significant members of the large numbers, and very well-known people who've been burned in the sense that funding for these, the way you build a science community is not just money, but it is associated with the amount of dollars and the length of time. You need to guarantee people that they're going to be able to get funding to do this type of work for long enough to make substantial, what scientists live for, to make substantial findings within their community. However, there's also, I think there's a chance to rebuild this community. And as it was built 15 years ago, which is with a real assiduous focus on bringing young people into the community. Everybody's going to watch and see were this to be funded at any level again as to whether or not the United States in particular were serious. It's clear that the European community and the Japanese community have been serious. They have their funding levels have gone up and down somewhat, but they have maintained a community. We have not really done that. However, I don't see any reason why you couldn't do that in the future, through a number of ways, and commercial is clearly one of them. Yes.
Well, thank you very much for your comments. We're very appreciative of your time, and let's turn to the subject of earth sciences, and our speaker will be Anthony Genetos. Good morning.
Thanks very much. Could I have the first slide? What I would like to talk about today, and thank you for the opportunity to speak, is the first decadal survey that has been done for earth sciences and applications. Can I have the next slide, please? The vision for this study was and I'll simply read it to you. It's understanding the complex changing planet on which we live, how it supports life, and how human activities affect its ability to do so in the future. Is one of the greatest intellectual challenges facing humanity. It is also one of the most important for society as it seeks to achieve prosperity and sustainability. Let me just pause for a moment and tell you something about some of the background for the study and something about the participants, if I could have the next slide. The background, this study was commissioned by NASA, NOAA, and the U.S. Geological Survey. Its charge was to recommend a prioritized list of missions, observations, and supporting activities to support national needs for research and monitoring of the entire Earth system during the next decade and beyond. This was the first decadal survey that's been done for the earth sciences, it was governed by a steering committee of 18 members, composed of 7 thematically organized study panels, each of which had about a dozen members or so each, ranging from an overall panel on earth science applications and societal needs, which I was fortunate to chair, ranging to land use change and ecosystem dynamics, weather, climate variability and change, water resources and the hydrologic cycle, human health and security, and solid earth, hazards, resources, and dynamics. Can I have the next slide, please? The objectives for each individual panel were to identify general needs and opportunities for spaceborne observations to advance our science over the next decade, to propose programs or missions to meet those needs, to rank those missions in priority order, describe each one in terms of its scientific payoff, cost, and potential benefits, identify observations that could not be made from space but would be necessary to complement those observations, and to identify and comment on other essential components, everything from data management to power supplies, technological challenges, and management objectives. The executive committee was, in one sense, sort of a marvel of interdisciplinary scientific interaction. Rick Anthes, president of UCAR, and Barry and Moore, then at the University of New Hampshire, co-chaired the committee. We had atmospheric chemists, we had technical experts in remote sensing technologies, we had university professors, we had people from operational weather forecasting centers, we had people from the national laboratories in a very wide range of disciplines. All of the executive committee, many of the panel members had extensive experience both as principal investigators and in some cases, such as my own case, I had a decade's worth of experience working at NASA headquarters in the Earth Science program. The elements of the study task statement were first to review the status of the field, develop our own consensus on some of the top scientific questions, to focus environmental observations, taking into account a whole series of users of information and data in addition to the scientific community, and then make our recommendations. Next, please. These are the combination of the scientific and societal imperatives that we identified. The importance of understanding climate change and its impacts, certainly one of the greatest challenges both scientifically and from a sustainability standpoint in today's world. The critical components of understanding ice sheets, sea level, and ocean circulation as a rapidly changing part of the physical climate system. Changes in precipitation and water availability, both for its scientific necessity for understanding the physical climate system, and of course, for the societal need of understanding where water will be available, not only today, but where it is likely to be available in future decades. The issue of transcontinental air pollution and both generation and transport, chemistry and transport, changes in the response and indeed the location of a whole variety of ecosystems in response to changes in climate, the critical nature of human health responses to climate, and the importance, both societally and scientifically, of understanding extreme events, both their location, their magnitude, and their frequency, in both the Earth system, the geological system, and in the climate system. Next, please. This is the first decadal survey for these communities, and was tremendously challenging. A huge organizational challenge was how to cover all the relevant scientific and application themes, as well as disciplines. It might have been useful in retrospect to have had additional panels focused on disciplines, in addition to the way that we were organized, but that perhaps will be something that a subsequent decadal survey may find useful advice. There are a large amount of multi-agency issues to confront in such a study, in which we wrestled with. This was a set of recommendations not just for NASA, but for the operational programs in NOAA and for the growing role of agencies such as the USGS. And thirdly, there were important changes in our baseline assumptions during the study. The budgets for Earth science during the period of this study declined quite dramatically. The NPOS program, the interagency program between NOAA and NASA and the Department of Defense, went through what we could only describe as a debacle during this time period, from which it is really only beginning to emerge. We actually issued 2 reports. Our first report was something that that our panel, or our committee, and the NRC decided to do. This was issued when after we had been working for about a year, I think. This first bullet is a quotation from the report. It's perhaps the strongest statement that I've ever seen come out of an NRC committee that I've had the pleasure of serving on. Today, the system of environmental satellites is at risk of collapse. I wish that were hyperbole. It was not. Since that time, and between then and for about 2 years afterwards, there were more delays, descoping, and cancellations of missions, both at NOAA and NASA. In the final report, what we recommended were a set of 17 missions phased over the next decade, and I'm going to come back to this in just a minute, intended in part to restore U.S. leadership in Earth science and applications from space, averting the potential collapse of the system of environmental satellites on which we depend, both for scientific insight, for a whole range of societal needs, and in fact for many operational purposes as well. We tried to represent this as an integrated suite of missions. We took recommendations from the panels. In fact, we had done a very large call for ideas and proposals. We had recommended to us well in excess of 100 potential measurements and missions. We worked for about a year on trying to identify what we thought were the most important of those. We sequenced those missions. We tried to match our sequence to the overall cost of that sequence to a combination of anticipated resources plus what we felt was reasonable growth in the Earth science observation programs, In so doing, we also took some pains to maintain the highest priorities, although I will say not all the priorities, of each panel. And then at the end of this, what we tried to do is issue some guidance on how to handle the inevitable budgetary or technology development problems. I have the next slide. Next slide. This is an overarching recommendation from the committee was that the Office of Science and Technology Policy, in collaboration with the relevant agencies and in consultation with the scientific community, should develop and implement a plan for sustaining global Earth observations. It should recognize the complexity of differing agency roles, responsibility, and capabilities, as well as some of the hard lessons that we've learned, both from, for example, the Landsat mission, the suite of missions around the Earth observing system, and NPOS. Next slide, please. For currently planned, what at that time were currently planned observing systems, we had two key recommendations: launching a global precipitation mission by 2012, obtaining a replacement for the Landsat 7 data before 2012. This is also known as the Landsat Data Continuity Mission. We also recommended that NASA continue to seek both cost-effective and innovative means of obtaining land cover change information. I have to say that this had particular relevance to me because during my career at NASA, I had the privilege of being the Landsat 7 program scientist. Next slide, please. Next slide. For NOAA, we recommended in particular an increased investment in putting research results and research observations in a truly operational program. Initiating missions for vector ocean winds, for GPS radio occultation mission, and for ensuring that we had total solar irradiance and an Earth radiation budget instruments restored to NPOS. For NASA, out of our 17 missions, we identified 15 in categories, in a sense in budgetary categories, but that are also phased in time. Next, please. I'll show you the spreadsheet of the missions in a minute. There's clearly not time to go through each one in detail. Let me share with you some of our additional recommendations for what are essentially managing such an ambitious Earth observation program. Several are related to technology development. NASA is going to have to continue to invest in both mission focus and cross-cutting technology development to both decrease risk in missions and promote cost reduction across multiple missions. We strongly recommended that a new venture class of low-cost missions be created to foster innovation and to train future leaders. Many of us, in a sense, grew up scientifically in the space program during a period in which it was essentially necessary to bet the major fraction of one's research career that a mission would succeed. Such a model is not, in fact, sustainable in the long run and an inherently risky business. And the original programs that were instituted to, in a sense, get out of that bind saw mission costs increase to the point where they were essentially as large as the previous large missions had been. Next, please. Secondly, to manage technology risk, what we tried to do was sequence these missions according both to budget risk factors and our assessment of their technological readiness. And that at this time, particularly for missions that we felt to be more challenging, which we then pushed to the right, that there needed to be technological investments made in order to try to reduce technological risk of those missions succeeding. If it turned out that there were insufficient funds to execute the missions in those time frames, it will still be important to make advances on the key technological hurdles and to establish that readiness through documented technology demonstrations before mission development phase. Next, please. Third, that we should leverage international efforts. Earth observation clearly does not occur in a vacuum. The Europeans, the Japanese, the Brazilians, and Chinese have active programs in Earth observations. And it's particularly important to leverage those efforts. There have been many successful examples of this in the past. OPEX Poseidon, for example. Our recommendation in this domain was to restructure or even defer missions if international partners themselves select missions which meet most of the measurement objectives. But if that is done, that it is critical then to establish data access agreements and establish science teams, which has not always been done in the past. And where appropriate, if an international partner identifies missions which meets our requirements, it may be effective for NASA to offer cost-effective additions to those missions. Next, please. We've heard the opinion of some since the study was published that the recommended budget envelope was outside the realm of practicality. In fact, the recommended budget envelope was essentially a return to the investment that NASA was making in Earth science observations around the year 2000. The notion that the United States cannot afford to have the same investment in critical Earth observations that it had a decade ago was a conclusion that we rejected. Nevertheless, this is the real world we live in, and there will always be budget pressures. And so what we tried to do in our programmatic recommendations was give some guidance to NASA and, in fact, to NOAA about how they ought to respond in the inevitable world that there are budgetary pressures, technological challenges that turn out to be more expensive than one could easily anticipate a decade earlier. First, by canceling missions that substantially overrun. Second, by maintaining a broad research program under reduced agency funds by accepting greater mission risk rather than by descoping mission and science requirements. To aggressively seek both international and commercial partners to share mission costs. And rather than evaluating mission by mission, the classical way of dealing with risk, to reevaluate the set of missions periodically. And in so doing, not doing this strictly as an agency activity, but by seeking broad input from the scientific community when that is done. I won't pretend to go through each of the 17 missions in detail. We've got everything in here from backscatter radars, to GPS radio occultation, to much more complex and challenging missions using with laser altimeters, and in the far future hyperspectral spectrometers for a wide variety of scientific needs. If I could have the next slide, however, rather than go through this. For each one of these missions, however, in the decadal survey, we've tried to do several things. And one is provide a detailed description of both the measurements, what we could anticipate in terms of instrumentation, what we could anticipate in terms of mission costs, and how one would use the measurements from each of those missions how they might be used to address both scientific challenges and challenges related to the societal benefit areas. Next slide, and this is my last slide. And then in addition, for each of the societal benefit areas, how the suite of missions, if implemented, could be used scientifically and in some cases operationally to begin to address those challenges. So let me stop there. There's a series of backup slides. The study was published the year before last. The initial response, both in Congress and in the agencies, was, I think, fair to say, quite positive. There have clearly been challenges in implementing it, both programmatic challenges and budgetary challenges. But several of these missions have already been selected for study, development, and the early stages of beginning to be ready for flight. Thanks very much.
Thank you very much. And before we take a couple of questions, I should acknowledge that one of our colleagues, Sally Wright, I think has joined us by teleconference. Sally, are you able to hear us?
Yes, I am. Can you hear me, Norm? I appreciate the opportunity to join you, if only by phone.
Terrific. Sally, thank you. And if you have any questions, please feel free to speak up. In fact, we'll give you first shot right now if you had anything you wanted to ask.
Actually, I don't, but I do want to thank the speaker. I thought that was a very, very interesting presentation on an extremely important and relevant topic.
I had a question I wanted to ask, and that would be, could you indicate to us the importance of human space flight in terms of the things you talked about?
In the discussions of the committee, we did not focus on primarily on the role of human spaceflight or the potential role of the ISS. There has been a tradition in the agency, not always for imagers, but for other types of measurements, of actually, in a sense, using the shuttle as a vehicle for doing launching pilot demonstrations. It's particularly true for some of the atmospheric chemistry missions and for the laser altimeters, where in a sense, what was turning out to be a regular or a quasi-regular access to space was useful for doing these kinds of pilot demonstrations.
Are there other questions? Chris?
Thanks, Norm. I should have said when the last speaker spoke, just to thank all the science speakers today. Because of the pace of this committee, I know that all of you have had to come here on short notice and put together presentations. So it's really an impressive job that everyone's doing. In 2005, there were a lot of reports in the press about cuts to the Earth observing budget, putatively driven by human spaceflight overruns or needs for growing budgets. I was struck that your group didn't identify any important missions that human spaceflight would enable, and it sounds as though you didn't focus on that question. I guess I have three questions. The first is that because your group simply didn't consider it likely that there would be very high priority missions that would be enabled by human spaceflight? And two questions. That and then my second question is, and as I said to the last speaker, don't let me put words in your mouth. Should we take away from the fact that you identified 17 missions and none of those have any important dependence on human spaceflight? Should we take away from that the single biggest thing we need to make sure with respect to Earth science observations is that human spaceflight not eat your lunch? Because we could make a recommendation that there be a firewall, and that the single most important thing is that human spaceflight do no harm in this realm.
I don't think you're going to find that quote in the report. I will say, and I think as with the previous speaker, these are my words, not the committee's words. The period of greatest progress, both scientifically and programmatically, for the development of the Earth observing systems that we have, essentially came during a time when there was such a firewall. I take away from that the existence of that firewall is critical for the continued development, implementation, and in fact the programmatic sustainability of a system of measurements on which in fact we depend and will continue to depend.
We have time for one more question. Leroy?
Yeah, kind of just to keep on the topic of human spaceflight and Earth observation, as I'm sure you're well aware that astronauts take tens of thousands of photos. In fact, on my ISS mission, I took over 16,000 photos of the Earth. And we're told by scientists when we come back that those photos are appreciated and in many times, specifically targeted cases, could not have been done better by a remote sensing satellite. And so, there's a little bit of a disconnect here, and I wonder if you could comment on that. Was it, again, kind of repeating what Chris just said, is it that you just didn't look at that element, or are we being flattered and our work really isn't that important?
Let me see how to say this, because some of my best friends have taken those photos. The photos The photography is important. It's a visible means of it's a set of information that is important for public acceptance, for getting a visual sense of what is happening. In terms of actually doing quantitative analysis, it is, I think, marginally useful. The ISS is in fact not a very good platform for consistent quantitative observations of the Earth's surface. It's not stable enough. Ephemera are not as well known as they are for the robotic platforms. It has because of the orbit, you can't actually see the whole Earth, and so for many of the applications on which the community, both the scientific community depends, and on which the operational communities depend, it would not be the first choice. It's not to say that opportunistic observations from that platform don't have a role. I think they do, and they could. But what we were really trying to do was identify the set of missions that we could not, that in our judgment, we could not and should not do without.
Thank you very much for your
Thank you.
comments. We appreciate it. Let's turn to the subject of astronomy and astrophysics, and our briefer will be Marcia Wright.
And I'd like the first slide, please. So astronomers have done decadal surveys for a long time, and in fact, we have just started last December our 6th such survey, and we're calling this one Astro 2010, and it is to set the priorities for the next 10 years for astronomy and astrophysics. And our sponsors, of course, are NASA, the National Science Foundation, and for the first time, the Department of Energy. And because we are midstream in this study, I want to emphasize that this presentation really represents my personal views, and one shouldn't construe that what I'm saying may have something to do with the final report. Obviously, I'm participating and know, but I want to be clear on that point. Let's go to the second chart, please. Astronomers have had a long relationship with human spaceflight. Of course, our flagship mission right now, the Hubble Space Telescope, would be nowhere if astronomers, if astronauts had not been willing to risk their lives to fix our telescope. And it's an understatement to say that astronomy is very grateful to that. We also have a long-standing tradition of using the moon when appropriate. Astronauts left retroreflectors on the moon's surface, and a very long data set has been gathered that have allowed a number of interesting tests of gravitational theories using those data. And so we can see that over 40 years we've had a relationship with the human space program. Let's go to the next slide, please. And there are some regions where there are areas of research where there have been very unanticipated connections between what we've learned as a result of, for example, the lunar samples that astronauts brought back from the moon, and how that now is connecting with research that is ongoing. The plot that you see in the lower left corner shows the age in mega years of some stars, and what's plotted in the vertical direction is how much, essentially how much material is still orbiting those stars. And you can see that there's a very rapid decay over a few hundreds of millions of years of that material. And if we then go and look at the upper plot, that shows the rate of cratering within the solar system, and the rapid decline of crater formation is on approximately the same time scale as what we see in terms of clearing of dust around other stars. And the stellar time scales come from other astrophysical considerations, and the solar system time scale comes from radioactive age dating of the lunar rocks. And who would have thought that rocks collected in 1970 would have a bearing on research that astronomers are doing with the Spitzer Space Telescope now. So you never know exactly what connection might come out of things, but I find it remarkable that these two different timescales can now be tied together to reach a conclusion about how planetary systems may be in their initial stages of formation in this material around the other stars and so on. Let's go to the next slide, please. You asked two questions that you wanted scientists to answer. And the first was to give examples of important science objectives that the human space flight program could address, for example, in the next decade. Now, when NASA chartered Astro 2010, they did not ask us to address the impact of human space flight or how we might take advantage of it directly. But we've received over 400 inputs from the broad astronomical community. We asked for white papers on technology development, science, missions. And a few of these mention a connection with the human space flight program. These were not connections, that we directly requested. This just came out of what the community is thinking. And a sampling of these ideas are placing new retroreflectors on the moon that would enable even more precise measurements, deployment of radio telescopes on the back side of the moon, which is a very ambitious program and I think would probably be not in this decade, but several decades hence. And the use of newly developed launch vehicles for astronomical missions. I'm sure you're all aware that astronomers are nothing if not ambitious, and the bigger the rocket, the bigger the telescope we can think of putting into space. But there were actually some other clever ideas for using some of the launch vehicles. There's one proposal in our stack of items that I didn't put on the slide, but it's to put a laser on Phobos to send back pulses so that one gets around having to send the light to there and back as you do with the lunar retroreflector. So there's some connections here, but I want to, we haven't reached a conclusion of which of these ideas we might support in the end, what would be the most important to astronomical research. But I have to say that it would be unfair to say that astronomers are demanding humans in space for their research programs based on what we've received from the community so far. There are places where astronomers will take advantage of the opportunities if there are things there, but there isn't something that's absolutely demanding that a person be there. And of course, there's some engineering connections. What Hubble has taught us is that it's very convenient if astronauts can go visit your telescope. And so with the trend to moving toward telescopes that would be in positions like the L2 point, being able to get there and do something might be a very useful capability. Let's go to the next slide. Your second question was how science and exploration could be mutually supportive. And of course, this is a question where I think astronomy and human spaceflight share a lot together. Astronomy, of course, is essentially the exploration of places that we have no hope of getting to, but there are very many connections with that work and where we can go explore. So, for example, if you go through these many responses that we've gotten from the full community, many now are looking for other solar systems outside our own. And one might almost characterize this as becoming a big business in astronomy now. There are many, many different thrusts in terms of trying to find planets around other stars. And the planet discoveries are accumulating very rapidly. The recently launched Kepler mission will actually, we hope, quantify the number of Earth-like planets around other stars. And a new field of transit studies where a planet in orbit around another star actually eclipses it. From our point of view, one can learn a lot about that planet from careful study of those data. And another connection between astronomy and human spaceflight comes in the realm of studying violent events, both violent events within our own solar system caused by the sun and those caused elsewhere in the galaxy, but which can have an effect on the near Earth and inner solar system environments. And so that's a realm where what astronomers want to learn sheds light on human safety factors, and I think it's safe to say that a lot of the solar research that has been done on flares is quite relevant to human spaceflight. Let's go to the next slide. Just to give you a sense of this discovery of other planets, you can see how quickly the number of planets being discovered has gone up since the initial discovery in 1989 to now. And of course 2009, the bar isn't very high because we're not all the way through the year yet. The different colors indicate the different strategies for finding the planets. And if you go through the list of planets being discovered, ones as small as Uranus and Neptune sizes are now being found. So we're getting close to the holy grail of finding an Earth-sized planets. And as I mentioned before, transit observations are giving us detailed information on the atmospheric characteristics of other planets. Let's go to number 7, please. So what are the goals for astronomers in this realm? They are to find other planetary systems that look like our own solar system. And the plot in the upper left shows a blue band that's the habitable zone, and with our own solar system at the top, and then a depiction of a system of 4 planets around another star with the unattractive name of Gliese 561, which just happens, Gliese was the man that cataloged the star. It's a cooler star than the sun, so its habitable zone moves in a little bit closer to the star. And you can see from the numbers there that planets only a few times bigger than the Earth have been found around this star. And in fact, one planet does appear to be within that star's habitable zone. And that's an active area of research to find out what the characteristics of that planet might be. Can we see evidence for water and so on? And the picture in the lower left shows the orbits of planets around another star that mimic what our own inner solar system looks like. And of course, the big picture questions are, how do these planetary systems form and evolve? What can that tell us about our own solar system? And conversely, what can studying our solar system tell us about these others? Can we find evidence for life elsewhere? And understanding our own planetary system is essential for informing these kinds of astronomical goals. Let's go to the next slide, please. This is a very complicated slide, and I won't go through all of the data sets here, but one thing I want to just impress on people is that the plot on the upper left shows data taken by the Hubble Space Telescope studying a planet that transits another star, and the pattern of dips and brightnesses with wavelength for that observation matches best with methane and water. And if you look at the plot in the lower left, there are 2 spectra from Pluto and Charon in our own solar system, one of which is largely covered with water, the other one of which Pluto, the spectrum is dominated by methane. And by comparing what we see from our own solar system to other planets, we're going to learn much more about each of them. The picture on the right is some more data from the Spitzer Space Telescope, where we're actually, by using this transit technique, able to map out the temperatures on the surface of another planet, and to get a feeling of whether the rotation matters the most, or atmospheric circulation and so on. And I find it remarkable that we can learn that much about a planet around another star, and we can then begin to compare it with what we learn from the different circumstances within our own solar system. Let's go to the next slide, please. Now, the other topic I mentioned where there's considerable mutual interest has to do with what we might call violence in the universe. And of course, the closest to home violence comes from our very own sun. And it's a very active area of research to try to understand exactly what it is that causes the 11 and 22-year solar cycles, what causes the sun's magnetic field to change the way that it does? How does all of that cycle drive in detail the formation of flares? What is it that makes a coronal mass ejection actually happen? Why doesn't that happen from all of the active spots? And it's a key goal for solar physicists to be able to predict why these things happen. And obviously being able to predict rather than just look and see that there's a sunspot group that might cause a problem, being able to actually predict would be much, much more satisfying for safety of humans in space. And there's a lot of hope in the community that the advances in numerical simulations and larger data sets are going to be able to get us much closer to this predictability goal. And for looking at long-term time in space, there's a question about whether the solar cycle now is representative or not. And by studying the cycles of other stars, like the sun, we may also be able to shed light on that question. And interestingly enough, looking at the solar cycle, or the equivalent of the solar cycle on other stars, is actually a byproduct of searching for planets, because this key technique of looking for repetitive changes in a star's output by transits, for those astronomers, the star's intrinsic cycle, like our sun's solar cycle, is kind of a weed and an annoyance, but it means that you've gathered a lot of other relevant data for understanding those kinds of cycles. Let's go to number 10. And we already know that there are a lot of galactic cosmic rays that come through our solar system and are clearly a hazard to people in space. And that studying those kind of cosmic rays has been something that astronomers have done for a long time and will continue to be a target of study. But we've recently discovered that there's some other objects in the universe that are much more dangerous than we might have originally ever thought. We've known for a long time that objects emit lots of X-rays and gamma rays. And in late 2004, there was an object called a magnetar, or a magnetized neutron star, a dead end of the evolution of a star somewhat more massive than our sun, emitted a flare of gamma rays that was so strong that it actually disrupted our atmosphere down to a depth of about 20 kilometers. The peak strength of this flare was really only registered by particle detectors on a mission designed to study the sun, largely called RESI, and its particle detectors could still function and detect these gamma rays at the peak, and then other satellites unsaturated and came back online. This object was way on the other side of the Milky Way from us, and I believe there was an estimate that it might have caused as much exposure to someone on the space station as a dental X-ray. This turned out the space station was on the opposite side of the Earth when this flare went off, so it didn't matter anyway. But if you imagine that we don't have a very complete census of these kinds of objects, if there were ones significantly closer, and there's certainly a lot of candidates within the Milky Way, it could be an unpleasant experience to have that many gamma rays go through you. They might be easily shielded from, but just another thing to keep in the back of one's mind, that there may be more hazards than we're used to thinking about. Let's go to the next slide. So I want to summarize by saying that astronomers have welcomed past opportunities to take advantage of what human spaceflight offers in terms of opportunities. And we will no doubt take advantage of the opportunities presented in the future. I have to say that there may be some budget issues if we want to piggyback something on and we have to pay the entire cost of a human spaceflight, that we'll have to discuss what those kinds of budget issues might mean. But the mere fact of humans going into space present opportunities that astronomers will no doubt take advantage of. And if I tried to predict what the most significant scientific result from such an enterprise would be right now, I think I would be undoubtedly wrong. That's the lesson from the past, that things you don't predict end up being the most interesting. And I think these two topic areas that I highlighted, studying planets around other stars, searching for signs of life from those planets, and studying the violent universe are areas where there's a lot of mutual interest between astronomical research, and human spaceflight. Thanks.
Thank you very much. We have time for about one question. Would anyone want to raise one? Since you're our expert here, please.
So I'll thank you very much for that presentation. I'll try to do the same sort of thing I did with the last two presentations. What I'm taking away, if we think about figures of merit for possible architectures, what I'm taking away from this is twofold. One is architectures that would favor an ability to service astronomical observatories, including astronomical observatories at Lagrange points, would be favored by your community, and besides that, do no harm.
Exactly, and I think we would also favor the ability to get detailed sample returns or chemical evidence that we could relate to what we see from planets around other stars.
Does anyone else have a short question? If not, I think we're all set. Thank you very much for sharing your thoughts with us. And then we come to the final briefing of this series. That'll be on planetary science. Steve Squires will be presenting that. Morning, Steve.
Well, good morning, and thank you very much for the chance to appear before this committee. Like the other speakers, I should stress that my opinions are my own and do not represent the views of the National Research Council or any other organization. I'd like to begin by very briefly reviewing some of the most important questions in planetary science, as expressed in the most recent NRC Decadal Survey. These questions are significant because they were derived from scientific first principles, without particular regard for the means by which they might be answered. The complete list of questions can be found in the NRC report entitled The New Frontiers in the Solar System, an Integrated Exploration Strategy, and I encourage you to look at that report. I'll just mention a few of the highlights here. So some of the questions, like, what processes mark the initial stages of planet and satellite formation? What's the history of volatile compounds, especially water, across the solar system? What's the nature of organic matter in the solar system, and how has this matter evolved? Why have the terrestrial planets differed so dramatically from one another in their evolutions? What planetary processes are responsible for generating and sustaining habitable worlds, and where are the habitable zones in this solar system? Does or did life exist beyond the Earth? And there are others. These are big questions, and they span all of planetary science. Now, that decadal survey also described a suite of missions that could address these scientific questions. Again, a complete list of missions is available in the report. Those missions include a Kuiper Belt Pluto Explorer, that's a Pluto flyby, it's happening now. South Pole Aitken Basin Sample Return, that's a robotic sample return mission from the Moon. Jupiter Polar Orbiter with probes, a Venus In Situ Explorer, it's a Venus lander. Comet Surface Sample Return, Europa Geophysical Explorer, Mars Science Laboratory, and more. Now this, of course, is not an exhaustive list of the kind of missions that could be flown in the time period of interest to this committee, but it does illustrate the breadth of techniques that have to be applied to answer the most important scientific questions identified by the NRC. The first point I would like to make is that most of the missions that address important questions in planetary science would not benefit from the presence of human explorers. Planetary flybys, planetary orbiters, atmospheric entry probes, landers to environmentally hostile bodies like Venus are all best done robotically, and I believe they will continue to be. However, there's an important subset of planetary exploration that can benefit from human spaceflight, and these are missions to the surfaces of solid bodies whose surface conditions are not too hostile for humans. Now, it's conceivable that in the distant future, humans could explore some planetary surface environments that seem too hostile today, including things like the polar regions of Mercury, moons of the outer planets, comet nuclei, and so forth. But for the time period of greatest interest to this committee, I believe that humans can only realistically explore the surfaces of the Moon, Mars, and some asteroids. And I will therefore restrict the remainder of my comments to just those bodies. Now, much has been said about the relative merits of human and robotic space exploration. My own opinion is that both have advantages and disadvantages, and that given sufficient resources, the best approach is one that uses each in the most effective way. My own personal views on this subject were shaped in part by my experiences doing research in ice-covered lakes in the dry valleys of Antarctica. There we used robotic techniques, a remotely operated underwater vehicle, to perform the initial exploration of the lake bottom. The The robot provided a safe, effective, and inexpensive way of answering the most basic questions about a very complex and hostile environment. After those questions had been answered, we then used scuba gear to investigate the lake bottom ourselves. The key point is that the first order knowledge that we gained from the robotic exploration allowed us to make expensive and hazardous dive operations, EVAs if you will, much more scientifically productive than they would have been otherwise. Armed with the knowledge that we had gained from the robots, we had well-defined objectives and plans for each dive that let us tackle the most complicated questions on the lake bottom very quickly and effectively. Now, given enough time, could we have built robots that could have done the same jobs that we did in our scuba gear? Yeah, probably. But we would have needed many cycles of design, use, and redesign. Humans have an extraordinary ability to function in complex environments, to improvise, and to respond quickly to new discoveries. Robots, in contrast, and this is a key point, do best when the environment is simple and well understood, and the scientific tasks for that robot are well defined in advance. There are also lessons, I think, to be learned from the missions of the Mars rovers Spirit and Opportunity. One is that rovers like these accomplish their tasks much more slowly than humans in the same environment would. What Spirit and Opportunity typically achieve in a day, a human explorer could do in less than a minute. The Opportunity rover has traversed about 17 kilometers in its 5.5-year lifetime on Mars. This is less than the distance covered by 2 astronauts in their lunar roving vehicle in a single EVA on Apollo 17. The rovers have other limitations as well. Spirit and Opportunity, of course, have exceeded our wildest expectations regarding longevity, operational flexibility, and science return. But they have also encountered challenges for which they were not designed, and that they consequently have been unable to meet. The rovers can't dig deep holes in the regolith. They cannot climb and descend steep slopes. They cannot turn over rocks. They often cannot position their cameras where they're needed most. And they cannot traverse some common forms of loose debris on Mars without getting stuck. All of these limitations have impacted their science returns, and all of them arise from the complexity of their landing sites. Again, given enough time for multiple design and redesign cycles, all of these problems probably could have been solved robotically, and probably could be resolved robotically in the future. But humans in the same environment could adapt to this complexity much more effectively. These experiences raise an important point. Because the capabilities of humans most surpass those of robots in complex environments, the scientific value that humans add is in proportion to the complexity of the environment that's being explored. That's a critical point. So which bodies are complex and which are less so? The moon's an airless body. It's experienced mostly impacts, volcanism, and modest tectonism over its history. Only impacts have occurred recently. Asteroids are more poorly understood, but are probably broadly similar to the moon in their complexity. Mars, in contrast, is a much more complicated world. It's experienced all the geologic processes that operate on the moon and asteroids, and many more. Wind transport, deposition, water transport and deposition, glacial and paraglacial processes, widespread tectonism, and others. Aqueous alteration and hydrothermal activity have yielded complex mineralogy on Mars that holds clues to past environmental conditions. And there are intriguing clues that Mars once had habitable conditions at its surface and may have habitable niches below the surface even today. All of this complexity means that human explorers can, in principle, contribute more to the scientific exploration of Mars than they can to any other body in the solar system for the foreseeable future. Now, given the strong scientific appeal of Mars, it's reasonable to ask whether or not there is high-priority science to be done at the moon. Looking at the most recent planetary decadal survey, the answer to that question is an unequivocal and emphatic yes. Several of the most important questions in planetary science deal with understanding how planets form, how they evolve, and why the terrestrial planets are so different from one another. Understanding the moon is central to these questions. That's why the South Pole Aitken Basin sample return featured so prominently in the last decadal survey report. That's why the GRAIL mission was recently selected as part of NASA's Discovery program. So there is unquestionably a great deal of important science to be done at the moon. It's my personal opinion, however, that most of the really important lunar science can be done robotically for the reasons that I outlined above. Now let me address 4 specific questions regarding the role of humans in scientific exploration of the solar system. First, if human explorers, are going to be sent to planetary bodies, what's the most cost-effective science that they can do? Second, what important science does sending humans enable? Third, what science can robotic systems do to help enable human exploration? And finally, what can humans and robotic systems accomplish together? Regarding the first question, if NASA is going to take on the substantial costs and risks of sending humans to another planetary body, there are important scientific tasks that those humans can accomplish for relatively little additional cost and risk. Clearly, the best example is sample return. Human explorers are going to have to come back to Earth, and when they do, it will be relatively straightforward for them to bring samples back with them. Moreover, humans can do a better job than robotic systems of selecting and collecting samples, particularly on a geologically complex body like Mars. Now, let me stress that humans are not required to bring back samples from the Moon, asteroids, or Mars. That can be done robotically. But if humans are going to visit these bodies, collecting and returning high-quality samples is one of the most important scientific tasks that they can carry out. Laboratory instruments surpass flight instruments in quality, so the best scientific work will be done with well-documented return samples. And samples can increase in scientific value with time. Some of the best science ever done with the Apollo samples is being done today, using instrumental techniques that did not exist when the samples were collected by scientists who had not been born at the time. Next, I'd ask what high-priority science is enabled by the presence of humans, i.e. what simply cannot be done without humans there. The answer may be nothing if we're willing to wait long enough, again, enabling enough cycles of design and redesign of robotic systems. But there are some very important tasks that will require so much equipment and infrastructure that's hard for me to imagine it all working without humans on site to operate and maintain it. Perhaps the best example is deep drilling on Mars. If habitable conditions exist on Mars today, they may be restricted to depths of hundreds of meters or more, where liquid water is stable under current Martian conditions. Deep drilling could be one of the most important scientific tasks carried out on Mars, but the equipment required to do it could be very difficult to operate and maintain without humans. Robotic precursor missions can do much to enable human exploration, as was shown by Ranger, Surveyor, Lunar Orbiter missions that preceded Apollo. Orbital or landed missions can be used to select landing sites for their safety and for their scientific potential. Precursor landed missions can characterize the environmental conditions on a planet's surface and the threats that they might pose to human health. This could be particularly important on Mars, where fine airborne dust is pervasive. Precursor missions can also characterize the environment from an engineering perspective, allowing better design of vehicles, habitats, and suits for humans. And precursor missions can be used to search for potential resources, including ice and other water reservoirs on Mars, possible ice at the lunar poles, and materials ranging from hydrocarbons to metals on asteroids. Also, there can be valuable opportunities for humans and robots to work together in exploring planetary surfaces. The most recent space shuttle mission demonstrated this potential with 5 EVAs conducted in tandem with operations of the robotic arm on the space station, the robotic arm on the shuttle, and the arm on the Japanese Kibo laboratory. So as robotic technology advances, I believe that human explorers on the Moon, on asteroids, or Mars will make extensive use of robotic systems, just as the astronauts on the shuttle and space station do today. For example, astronauts in orbit or on the surface of asteroids or Mars will be able to teleoperate rovers without the long time lags and the need for autonomy that's required by teleoperation from Earth. Essentially, all of the science that humans will do on these bodies can be aided by judicious use of robotic systems, just as we used robotic systems to amplify the science return from our dives and the drive-outs. Finally, I would be ignoring a critical issue if I did not comment on the cost-effectiveness of human versus robotic space exploration. I have argued that humans, or humans aided by robots, can carry out scientific exploration of planetary surfaces, particularly complex ones, more effectively than robots alone. But if good science were the only goal, then I think one of the clear lessons of 50 years of space exploration is that robots alone are more cost-effective. There are a few examples like deep drilling on Mars of high-priority science that may never be practical without humans present, but there's more than enough important planetary science to be done purely robotically, including exploration of the surfaces of the Moon, asteroids, and Mars for decades to come. Also, I'm personally wary of arguments that say, in effect, we're going to do this anyway, so what science can we add to it? Such arguments have not served NASA well in the past. When science is an afterthought, it can be the first thing to go when schedules slip and when budgets get tight. Now, I do not mean to say that human exploration is bad for planetary science. It need not be, and I believe it should not be. And I am well aware that science is not the only motivation for human exploration of the solar system. Indeed, I am a strong advocate, personally, of human exploration for many other reasons. But if science is to be served well by a program of human exploration, then science must be a full partner in planning and executing that program. And if science is going to be one of the major goals of human exploration, not just an add-on, then care should be taken to concentrate the human explorer's efforts in the scientifically complex settings where humans can contribute most. Thank you.
Steve, thank you very much. And we have time for a couple of questions. I'll start out with one then, Steve. The story is told about Jack Schmitt on the moon. You obviously recognize the story by your reaction. He found a rock that a robot might not have distinguished from other rocks that were around, and that particular rock was extremely valuable in terms of our understanding of our scientific benefits from the mission. And that the moral of the story was that a trained geologist such as Jack could do things that a robot just can't begin to do. Could you comment on that?
Yeah, there is no question in my mind that having humans, especially experienced scientists, in the field, doing field work on another planetary surface adds value. And I think they will add value on the moon, they'll add value on asteroids, they'll add value on Mars. My point is, the more complicated the environment, the more value they add. And if they add some value on the moon, they're going to add even more in a more complex environment like Mars is.
Thank you. Please, Joe.
Sometimes I get the message lost in the careful euphemisms that we use to explain this. I'm going to say what I think you mean, and then you can tell me if I'm missing it.
Fire away.
What you're saying is, if we're going to send humans, don't just send them to the boring places because they're easy to land on.
That would be one good way of putting it, yeah. I think maybe a slightly more positive spin on that would be concentrate their efforts in the place where they can contribute most.
Steve, I'm actually left with few questions that are directly relevant to the science objectives, because I think you really addressed what the committee needed to hear or wanted to hear. I would like, though, to ask you to go back to a statement you made at the very end where you said that science is not the only or primary motive for human spaceflight. And I wonder if you'd share your thoughts with what you think the important motives for human spaceflight are.
Oh, well, there are many. And again, I stress that these are my personal views. Bob Zubrin earlier today very passionately expressed some of the other motivations for human spaceflight. There is, I think all of us feel a deep human need to explore, to go places where we haven't. I think it was described as a spiritual need, and that's significant. I will tell you personally, one of the things that I've been involved in for the last many years now is the Mars exploration rovers, Spirit and Opportunity. And like me, most of the people who built those rovers grew up during the 60s watching Mercury and Apollo and all that stuff on television and dreaming of sending spaceships to Mars someday. And now we get to do it. And so the inspirational role, the thing that causes young people to go into engineering and science and so forth, is important. And there are many others. It's not just the science.
And do you think those goals are sufficient to justify an $80 billion program over the next decade?
If it's $80 billion over a decade, yeah, I personally do. I personally think that those address pressing needs at a national level that justifies that kind of expenditure. $80 million over a decade, that's $8 billion, a year. And to me, that sounds like a darn good investment. The question is that what it really costs?
Steve, thank you very much. We appreciate your comments and your candor as always. We now have the privilege of hearing from some of our colleagues in Europe. The first speaker is from Ariana Space, and that will be Jean-Yves Le Gall. Morning.
So good morning, Mr. Chairman. Good morning, ladies and gentlemen. First of all, I would like to thank this August Commission for allowing me to address your committee as it considers issues of historical importance to the continued exploration of space. As you said, my name is Jean-Yves Le Gall, and I am the Chairman and CEO of Arianespace. Our company, Arianespace, is the first commercial launch service provider in the world. Our first mission was 30 years ago, and our latest mission was 30 days ago, with TerreStar 1, the biggest commercial telecommunication satellite ever launched. TerreStar 1 was nearly 7 metric tons, and we launched it to geostationary orbit. But even bigger than TerreStar 1 was the first ATV launch last year, when Arianespace hit a milestone and put the 19.4 metric ton ATV Jules Verne into low Earth orbit. After the ATV made its picture-perfect docking with the ISS 2 weeks later, members of the crew were able to bring aboard several tons of crucial supplies and equipment. Shortly after that, the ATV raised the altitude of the ISS, and it also did the unexpected in using its thrusters to slow down the ISS to avoid orbital debris. In the meantime, the ATV served as an extra room for the station. Its pressurized interior allowed the crew to use it almost as if it were another module of the ISS. This ATV launch was a major step forward that enabled the international partners to fully utilize the ISS to conduct important biological and scientific research in space. Now, we are looking for 2010, when we launch the second ATV named Johannes Kepler to the ISS, in support of a completed ISS with a full crew of 6 astronauts. We, at Arianespace, are very, very proud of the flawless ATV mission controlled by your colleagues at ESA and CNES. And with all due modesty, we were equally proud of the launch vehicle that put the ATV in orbit. The Ariane 5 has now been in operation for more than a decade, and since inception, the Ariane 5 has proven itself to be a reliable heavy-lift launcher. Originally human-rated, the Ariane 5 has adapted to its present-day role as a leading large-capacity launch vehicle for satellite operators and international partners the world over. But the Ariane 5 is not limited, as you know, to GTO launches. As I will point out in my presentation, the Ariane 5 can reach lunar orbit, the lunar surface, and Mars, objectives that are compatible with NASA exploration mission. We often tell our customers that launches speak louder than words. Let me say that the launches also speak louder than PowerPoint slides. We are a proven solution for providing cargo to the ISS, and I am here today to provide a short presentation on this topic. Now, please allow me to elaborate on these points. So you have here some slides. I would like to get the next slide, please. Next. Okay, so first of all, a few words on the mission. Today, as I said, with the Ariane 5 and the ATV, we provide the cargo services to the ISS through appropriate international collaboration in support of NASA's human spaceflight activities. Next. As you know, the baseline for the ISS utilization is first to support for 6-person crew aboard the completed ISS, the ISS utilization for biological and scientific research, and in 2010, the shuttle retirement will diminish the US upmass return capability until CRS supplier come online. So CRS, it has 4 independent parts, 2 launch vehicles, and 2 cargo systems, which must be operational by 2011, and the requirement for 20 missions carrying 48 metric tons of cargo between 2010 and 2015. So we see that NASA is likely to need gap filler commercial cargo service by 2013, should any of the 4 systems be delayed. And I think that there is likely a shortfall of 8 to 12 metric tons per year in 2012-2015. Next. A few words about our company, Arianespace. Since 1980, we placed space in the center of everyday life with launches for science, for Earth monitoring, for security, and of course for communications. And since our inception, we launched a total of more than 50% of operational commercial satellites. And as I said, the last one was TerraStar 1 in early July. Next. In our mission, in fact, we are committed to organize everything around the launch, and in particular for the servicing of the station, we have now in our order book 6 Ariane 5 launches devoted to launch VATVs. The first one has been launched last year, as I said, and the next one will be launched starting next year at a pace of one every 18 months. Next. Ariane 5, today this is probably the most reliable heavy lift launcher. We have now, since 2003, 31 successes in a row. We have a capability of 20 metric tons to low Earth orbit. It was the ATV mission. A capability also to lunar transfer orbit and to Mars. And this point is quite important because I think that Ariane 5 is a very well-suited launch vehicle for the exploration. We have a very good launch tempo with a total of 7 launches per year. And today we have 46 launch vehicles which are currently in production. Now, a few words about the ATV Jules Verne. Next. At launch, we had a total mass of 19.4 tons, and the Jules Verne has a capability to bring 840 kilo of water and 100 kilo of air to the station, 4.7 metric ton of propellant for ISS reboost, some 0.4 metric ton for disposal mass, and globally VATV has 3 times the capability of a Progress launch vehicle. Next. A few words about the mission overview. The Jules Verne arrived in French Guiana, our home port, in August 2007. We performed the launch last year on the 9th of March. We docked it to the ISS on the 3rd of April. There were some reboost firings on April 25 and June 20, and the mission lasted in September with the induct from ISS and the atmosphere re-enter. Next. You have here a comparison between the VATV, the Progress, and the HTV, and you see that for the cargo mass, we have a capability with the ATV of 7.75 metric ton. The cargo, as you know, is 3.2, and the HTV, which will be launched for the first time by our Japanese colleagues next month, in fact, is just 6 ton. Now, a few words about the international cooperation. We are performing our launches next from the Guyana Space Center. There are 2 points on which I would like to insist. We have very modern facilities meeting all Western safety standards, and this is in fact a NATO territory, which is also quite important for the launch of governmental satellites. Our next very important mission, besides the ATV, will be the launch of the James Webb Space Telescope, and we are very honored to have been awarded this contract by NASA and ESA, and it will be an heritage from Rosetta and Herschel Planck that we launched early this year. As a conclusion, next, I would like to say that I think that the Ariane 5 ATV cargo resupply can provide gap filler services until CRS providers fully meet NASA requirements. This is the first point. The second point on which I would like to insist is that this approach can sustain architecture for future US human spaceflight providing utilization of the completed ISS. The third point, Ariane 5 ATV is a flight-proven system, and I think that it is quite important because it is now fully available with Ariane 5, 31 successes in a row, and the perfect flight of the Jules Verne last year. And this available system, this flight-proven system, meets NASA's ISS cargo resupply requirements. And last but not least, I think that this is a very nice opportunity for international collaboration using a successfully demonstrated capability. I thank you for your attention.
Thank you very much. We do have time for questions. Jeff, would you like to start?
Yeah, thank you very much for the presentation. I have to ask this one very carefully so we don't say too much or too little. The ISS experience has demonstrated quite clearly that it's very advantageous to the robustness and sustainability of your program if you have more than one way of doing things, because then when one of them has a problem or has a slip or has an accident, you're not down to zero. I'm also aware that when you ask any commercial supplier, can you do fill in the blank, the answer is always, well, yes, if I have enough money. So I have to ask you to distinguish in this question between that which is sort of a reasonable stretch beyond where we are today and that which, of course, anything can be done for the right amount of money. We're faced with the task of looking at an array of launch vehicles. Some of these launch vehicles have more capability or more throw weight than others. It sure would be nice if we designed exploration elements and other launch providers could launch them, because then there'd always be more than one way to launch them. So within the bounds of reasonable sanity, how big can you go in the future?
See, as I said in my presentation, what is important for me, in my opinion, is that this system, Ariane 5 plus ATV, is fully available. And with Ariane 5, every 2 months, we demonstrate the reliability. And the ATV, we have a first flight which fully demonstrated the capability of the system. So it's almost an off-the-shelf system. And I think that this is the point which is the most important. Now, in front of us, we have plenty of Ariane 5 launches for commercial purpose. And it will be very easy to pick one of these launchers to be used for VATV. This is basically the reason why we plan to have 6 ATVs launches for ESA within the frame of the barter agreement between NASA and ESA, and we guarantee the reliability of the launch with Ariane 5 because of the successful commercial exploitation of Ariane 5. So I think that this is a fully available system, flight proven, and after this, we can, if a decision is taken to use the VATV for flights outside of the barter agreement, we need 36-month clearance for VATVs, and for Ariane 5, we have plenty of launchers which are ready to use.
Leroy?
Yeah, it's not really, sorry, we didn't, that's all good information and I'm very much interested in it, but that's not quite the question. The question is, what larger throw weight derivatives of the Ariane 5 can you reasonably foresee being developable over the next 5 to 6 years that might provide a backup or an alternative path to U.S. source launchers for elements that are larger than the ATV or HTV?
Today, Ariane 5 to launch the ATV is using its full capacity, which is about 20 metric tons in low Earth orbit. There are some plans to increase this capacity, but the decisions have to be taken in the next 2 or 3 years, and it will not be available before, let us say, the end of the next decade. Today, we have a system working with Ariane 5 and the ATV. For the rest, there are decisions to be taken, and of course, there are, after this, to demonstrate that the system will be flight proven.
Leroy?
Well, thank you for your presentation and for coming all this way to meet with us, and congratulations on the string of successes of Ariane 5. My question is about Ariane 5. I'm sure there have been some studies done. Can you comment on the qualitative difficulty of human rating in Ariane 5, and was the Ariane 5 perhaps designed with that thought in mind?
Today, at the beginning, Ariane 5 has been human rated, and after this, you know the story, the Hermes space plane has been cancelled, and now the vehicle is no longer human rated. So if it should be considered to launch with Ariane space astronauts, which may be a strategic objective for space, we will need to once again qualify Ariane 5 to be human rated. Today, this is not clearly in the plans of Europe. This is an objective, but it is not yet decided. And what we are focused on the ATV launches. We have 6 launches in front of us, and we started recently a study on the possibility to have a cargo return capability.
If one were to order an Ariane 5 today, how long would it be before one could launch it?
With Ariane 5 today, I missed your point. Could you repeat?
I'm interested in the lead time between an order and on orbit.
For Ariane 5, it is not a problem because we have plenty of vehicles which are ordered. The question is for the ATV, and for the ATV, we consider that the order has to be made 36 months before the launch.
I'm sorry, how much?
36 months, 3 years for the ATV. But for the Ariane 5, as I said, we have 46 launch vehicles which are in production, and we have plenty of launch vehicles which are available.
Any other questions? Bo, do you have a question by chance? All right, Sally?
Yes, I actually do have one, Norm. Thank you. I'm curious about your plans for evolution of the ATV. I think I heard you mention that you're thinking about it as a possible return cargo return capsule. I wonder if you could describe the timeline for that, when you would expect that to be tested, and whether you plan to consider evolving the ATV beyond that, perhaps for a rescue capsule from the space station.
She was asking about the return capability of an ATV and what the timelines were for that, and an associated rescue capsule capability.
There is now a study which has been started by the European Space Agency about the return capability of the ATV in changing the upper part of the ATV. I do not know the exact figures because the study are just starting, but this could lead to a decision in 2011-2012.
Well, thank you so much for sharing your thoughts with us. We appreciate your coming all this way.
Thank you.
Thank you. We then will hear from the European Aerospace and Defense Systems. Mark Kinnersley will be speaking to us. Mark, good morning.
Good morning. Thank you very much for the invitation. I think I can expand a bit more on the advanced re-entry vehicle during my presentation. Very much appreciate having the opportunity to address this committee for the review of U.S. human spaceflight plans. It's a privilege. EADS is very much encouraged by the serious interest shown by this committee in administration. If you could get to the next chart, please. In expanding US-European cooperative partnerships in this field. As your charter clearly alludes, the ability to develop and sustain a robust US human spaceflight program requires leveraging all alternatives available that can provide efficiencies towards affordability, risk, and schedule. We at EADS Astrium are confident we can provide a great benefit to NASA and to the US taxpayer by undertaking the following specific points which are contained at the end of this presentation, but I'll repeat them now. The automated transfer vehicle, EADS Astrium can offer additional ATV mission services to supply ISS in cooperation with the US industry. In particular, ATV can be specifically used to plug the potential logistics gap to the ISS after shuttle retirement. That's point one. Industrialization. EADS Astrium's expertise gained over the last few years as the industrial operator for Europe's ISS activities could further enable international operational programs to achieve reliable yet cost-efficient industrial services. We operate the ISS on behalf for ESA. I'm talking about the Columbus part, not the whole part. That would be good. But in future exploration programs, EADS could provide significant key building blocks in a joint international human and robotic space exploration scenario. I think we have many capabilities which I will show you in the next charts. EADS Astrium, as a multinational company that lives and breathes international programs, is convinced that partnership is truly the best way forward for both the US and Europe to realize their respective goals. We've been working together for 30 years, and I have no reason to doubt a successful partnership in the next 30 years. Next chart, please. I had trouble fitting a lot of these photos onto a PowerPoint presentation. Excuse me for the small writing. At the end of the presentation, there is a fuller description of all these different products that we have from EADS Astrium. I'm just going to go through it very briefly due to time limitations. We have here developed the Columbus Orbital Facility, which you can see in the top left-hand corner. This was done under a firm fixed-price contract to European Space Agency, you might add. The Ariane 5 launcher production development with a prime contractor for Ariane 5, and we have delivered on time and on quality to Ariane Space to do their 7 launches per year. The automated transfer vehicle, which we produce now in Bremen. The Johannes Kepler is well underway to being ready for the 2010 launch. We manage the European contribution to the ISS as the industrial operator, and we've also performed atmospheric re-entry, descent and landing. We've led a lot of the ESA interplanetary missions like Mars Express and Venus Express. And in the future, we're looking at developing the ATV further, what we call ATV Evolution, or the Advanced Re-entry Vehicle. This will initially replace the integrated cargo carrier with an Apollo-shaped capsule, which will allow cargo to be downloaded from the ISS initially just for cargo. And eventually, this could eventually be used as a human-rated vehicle. We have got a study from ESA, which we have just started, which we hope to answer a lot of these questions about exactly what the vehicle is going to look like, the precise definition, and also the potential questions on human rating of Ariane 5. Soft and precision landing and extended mobility on the surface of the moon, we're investing a lot of money in that. We've also started an ESA study on that. In fact, we've also got a study from the DLR to do an earthbound demonstrator test for soft and precision landing. Next chart, please. We're very extremely, as I said before, we're extremely experienced in partnerships with NASA and US. We have subsidiaries over here. We can be counted as reliable and trustworthy. We've worked with the US on the Space Lab missions, I think if I remember correctly, 22 since 1983. And we are now introducing ATV as a regular operational vehicle. It's now operational. Next chart, please. We really want to reap the benefits of the ISS investment, and this means it's time now to realize the fruits of our joint labors and use this rather unique facility. In 2008, European theory became reality. It was a great year for Europe in this field, with both the launch and successful commissioning of the Columbus Orbital Facility and the successful maiden voyage of the ATV. Europe arguably came of age in this human spaceflight in this year. This brings confidence to prospective partners, especially when you consider the vehicle. I haven't got a diagram here showing the sizes, but it's the size of a London double-decker bus. I'm British, so I'm going to use the double-decker bus analogy. Successfully managed to formation fly and dock inch perfect. Notice against the use of inches, I'm British again, with platform travelling at 17,000 miles an hour. So I just want to make the point, this thing has flown, it's proven, it's available. And a capacity over 7 tons. And it's soon to be one of only a handful of operational vehicles available for logistics. So plainly spoken, ATV is available and can expand its already major role in ISS logistics supply until a new US system comes online, and could potentially even be flown on US launches. We've done some preliminary studies on that, and this could be compatible. In addition, an evolution of ATV towards a download capability with the development of ESA's Advanced Return Vehicle could ease a strain on download logistics. Additional partner capabilities, as made before the point, make the system more robust. We also think we can help with the utilization because of our experience in payload production and management there. And last but not least, EADS will fully support efforts to have the ISS lifetime extended as far as possible. Next chart, please. The US should also consider leveraging European capabilities, other capabilities. An international space exploration initiative will become more robust and vigorous through contributions of the partners. EADS Astrium's developments within ESA-sponsored project to land soft and precisely on the moon, we started a feasibility study on that, could perhaps lead to a European automated cargo lander for the moon, launch an Ariane 5, which could bring nearly 2 tons of usable payload mass to the surface of the moon, and this would then spread the burden and share the costs for a return to the moon, for example. Additional key building blocks could be used the ATV to based on the rendezvous capability of ATV for other aspects, such as rendezvous techniques for sample return or for approaching near-Earth objects, for instance. And last but not least, I'd like to just stress that Astrium has been operating the ISS, the European part of the ISS, on behalf of the European Space Agency, and I think we can bring a lot of lessons learned into this to show how we have industrialized this and run a European team of industry there to operate the European part of the ISS in a reliable yet cost-efficient manner. Next chart, please. Again, to summarize the conclusions I made at the beginning, and please, there's some more charts at the end if you need more information on some of the other aspects. EADS Astrium can offer additional ATV mission services to supply ISS in cooperation with US industry. Industrialization, we think we can bring a lot of lessons learned there from our side to industrialize this, to save taxpayers' money and to provide reliable yet cost-effective, efficient services. And for future explanation scenarios, we have a lot of capabilities which could provide significant key building blocks to a joint international human and robotic space exploration scenario. I'd like to thank very much for your time to the committee and to the audience and for your attention. Thank you.
Well, thank you very much for your comments, and we do have time for a couple of questions. Wanda?
Good morning, and thank you very much for sharing your tremendous track record for EADS in support of the European operations. My question is, we talked about the benefit of leveraging the partnership for ISS. My question is to ask you to speculate for, sort of 30 years beyond that, what would be the vision for a successful partnership relationship? What are the things that you think would make that attractive? Certainly for your organization and maybe for the European partnership. Specifically, if you could address whether you've given thought to operations at Mars or NEOs and what would be some of the challenges there.
Okay, I've just got to make plain that I'm speaking for EADS Astrium and not for the European Space Agency, for European government policy, so I have to be rather a little bit careful on that because this has to be decided obviously by the government and by ESA. Having said that, yes, we've actually been working very closely with NASA, and my team, especially in the advanced projects area, have been working in an architecture study with ESA. These results are available on the internet, actually. They were presented in Frascati last year, so I would certainly direct you towards ESA. I think we undertook a lot of those studies, probably 50% or something like that, and various aspects of the whole architecture, including Moon, Mars, LEO, etc., was exhaustively studied there, and in fact we had US industry participate in one of the studies with us as a consultant, so we are actively looking at that. I would just suggest you go to the website. I can give you that later.
No particular benefit, one way or the other, from an industrial operator perspective?
I think you know, we've just started this industrial operator aspect for the Columbus part, and I think we've learned a lot of lessons at the moment. I'm sure we can share that further if there's further questions, and we can arrange certainly meetings about that. But I certainly think this is the way to go. It's certainly with Ariane as well. We've industrialized that a lot as a prime contractor, and I think this is certainly a way to go in terms of achieving great efficiency.
Thanks very much, Mark.
Yeah.
I'll be careful to phrase this as a technical question so that it doesn't get into the questions of ESA policy. There's a lot of possible exploration architectures in which you could do a lot more exploration earlier if you had a very capable, storable propellant Earth return stage that you could, you know, send things to places in the solar system and use this Earth return stage to get them back again. It has struck me that you could derive something like that from the industrial infrastructure of the ATV in a relatively straightforward manner. Does that make sense to you?
Yes, definitely. Yes, you've been reading my stuff. No, we may make a lot of thoughts about that. That's what my team does every day. ATV is a great vehicle, and I think we can certainly base things on that, definitely.
If you have studies or papers on that you'd like to share with us, I think that would be welcome.
I will certainly go back and do that.
Are there any other questions from the panel?
I have one.
Please, Bo.
Thank you for your comments. I have a question. Can you envision any single country undertaking in not too distant future a mission to Mars with humans? And if you think it has to be an international affair, which country should lead?
On the personal question, personal basis, I think clearly the US is the leader in human spaceflight within the world. I mean, I've worked a lot in Russia and have a lot of respect for other countries' capabilities. I do think a human mission to Mars would benefit from international cooperation, and I think clearly the US is as a leader in that, for my opinion.
Sally, anything from you?
Yes, I do have one technical question that regards the ATV as a cargo resupply for ISS. I recognize that there are 5 additional launches planned of ATV, and I wonder what the capability would be to add additional launches. In other words, what's the production capability of ATV? Are we restricted to those 5, or is there additional opportunity for further flights?
Right, thank you for the question. I thought that might come up. Yes, I mean, we currently have a production line set up in Bremen, and the lead time, as Jean-Yves Legar mentioned, is 36 months for an ATV. So if you would like one, say in 2011 or whatever, you've got to act pretty quickly. So 2011 is probably cutting it fine. But certainly, yes, we think we have the flexibility to provide more ATVs. And certainly we plan on doing that in the future, because if the ISS is extended, we will need more ATV missions anyway to contribute to European compensation operating costs. So I think there's flexibility certainly to produce more ATVs.
Quick follow-up. At what rate?
Okay, what rate? Again, it depends on how you set up the production facility, because we have optimized it for the current setup as it is, which we're doing 1 per year, but certainly I'm sure we could accelerate that rate, but this has to be investigated.
Well, again, thank you very much for sharing your thoughts with us. We appreciate it.
Thank you very much.
Osterly from the University of Michigan, and there are 2 microphones on either side. Aaron.
Thank you, Chairman Augustine. As you said, I'm studying at University of Michigan, and I look up there and I see a lot of gray hair and a lot of the older generation. No disrespect.
We would be lucky to have gray hair.
No, just yeah.
Hey, watch it.
Thank you for the compliment.
Do you plan to have a doctoral exam soon?
But but I think it's interesting that the person who will be making the final decision is younger than many of you, and my generation, which will be paying for and either embracing with or dealing with the proposals that come out of the Augustine Commission. We will be the ones that have to face those decisions. And last week during Cocoa Beach, you guys or the Beyond Leo subgroup proposed making the big thing was make us a spacefaring society, and I was thrilled with that. But you can't promise that to my generation. We're not Apollo worshippers. I wish we were, but we're not. And so if you propose things that are out of budget, and you don't have a discernible, a granular, predictable, and measurable return on investment, it won't get funded. So I would ask you to not, A, don't promise more than you can honestly expect, and B, don't expect that we're going to get any sort of massive increase in funding. I would love to see it. I really would. But I'm a realist, and I don't see it happening for my generation. And those are my comments. Thank you.
Thank you very much. Let's go to the next speaker, who will be Jeff Fitzsimmons from USAF Retired.
Yes, thank you for allowing me to make the comments today. I have a few recommendations for the committee, but I'm speaking just for myself. I'm retired military and semi-retired aerospace engineer. Here's my recommendations. Number 1, full utilization and use of the International Space Station should be the #1 priority for the human spaceflight. For the next 5 years, it will be our human spaceflight priority. It's the only affordable one in the current budget projections. It has the greatest near-term benefits and relevance to the American people, and it's achievable with modest investments in utilization funds. Recommendation number 2, $1.0 billion over the 10-year time frame. That's $100 million per year, specifically for ISS use and microgravity science missions. 3, extend the appropriations and commitment to ISS until 2020. Makes no sense to try to decommission the ISS in 2016 if we're going to fund something like COTS. 4, set up an independent organization to manage the ISS utilization, such as the Hubble Space Telescope Science Institute does. 5, reestablish Space Product Development Group and re-energize the commercial space centers to promote ISS use. 6, establish objective success criteria for microgravity science benefits. 7, use the ISS as a bridge to Mars, such as long-duration missions or a variable gravity centrifuge. And 8, above all, name it. Let's name it something sexy. I propose something like the Isaac Asimov or the Arthur C. Clarke, or calling it Excelsior. In sum, it's the #1 priority because it's affordable, it's achievable, it's relevant, and has direct benefits to the American people. Thank you.
Thank you. And I see more people standing here than we had signed up, but I must apologize. We really are pressed for time today. So if you didn't sign up, we would ask that you communicate with us by our website, which is
http://hsf.nasa.gov. I need a nickel every time I say that. I would not need to be employed anymore.
You got it. Thank you. So we'll continue with the people who have signed up, and that'll be all we'll be able to take this morning. The next is John Casanto from ITA.
I might, thank you. I'm going to give you 5 points relative to the return vehicle from Mars. There's a briefing that all the panel members should have that I've given to Mr. Philip McAllister. So you've got that someplace electronically. It's obvious that there's a strong support for a direct mission to Mars, bypass the moon. Buzz Aldrin has said that makes sense. Robert Zubrin has said that makes sense. If Mars is going to be the next national goal of this nation, we've got to make some changes. You want to get rid of, you want to scrap, you want to replace the CEV Earth entry configuration. Why do you want to do that? It's a low lift-to-drag ratio vehicle, and what it does, it severely limits the various Mars mission option scenarios. And again, the briefing I've given to Mr. McAllister has all the technical data. You can't do anything to the Apollo configuration, the CEV. You can't do anything to get the lift-to-drag ratio up. And the bottom line is there have been a couple of studies done that have shown that a mid-L over D vehicle, a lifting body, has enough lift-to-drag ratio to do all the foreseeable Mars missions. These kinds of configurations have been studied. They've been flight tested. It would seem to me the Commission would want to look at this, take a real hard look at this, and don't just take what's left over from Orion and Constellation. Look at it and say, hey, is there a better way to do it? Why would we want to go to Mars and limit our mission options? And if you fly the Apollo configuration, you can't do all the missions. Finally, there was a reentry vehicle compendium study done 3-4 years ago. We looked at every configuration on planet Earth, everything. We got the aerodynamics, we looked at the trajectories, we got the shapes. So we know it's flown, we know it's there, we know it's easy and quick to do. You don't have to go redesigning and reinventing the wheel. And the bottom line is the study conclusively showed you go to a mid-L over D vehicle, and there's several configurations. It's in the briefing I've given them, McAllister. And these things have flown. You go to these things, you meet every Mars mission. Bottom line. Thank you.
Thank you very much. The next speaker is Cindy Martin Brenner
Yes,
from
hi.
the American Society of Gravitational and Space Biology.
Yes, it's a mouthful. I have another compelling reason to be very fast here. I have a 12-year-old daughter who's having her birthday, and she's waiting for Mom to get home to open her present, so this is going to be very quick. Betsy, Dr. Cantwell spoke earlier today about our research community, Life and Physical Sciences community. We are the group, we are the scientists who have done this research since Skylab. We would like the opportunity to do the research on the ISS. As Dr. Cantwell mentioned, that there is an opportunity to rebuild this community. In the package that I believe you're going to receive from NASA or possibly the Senate Commerce Subcommittee on Science and Space, there is a paper in there written by the community, the scientists, that talks about how to do this, how to rebuild it. And I just really want to call your attention to this and their support and information from ESA, ELGRA, and Japan in regards to this. So just want to bring us to your attention. Right, thank you.
Thank you very much. And our final speaker from the public comment section is Carrie Bean from Texas A&M.
Howdy. I'm
Good to have an Aggie here.
Yeah. I've been really involved in outreach. I've worked on Spirit and Opportunity in Phoenix and eventually Curiosity in Hubble. And yes, I'm only a senior. And I've really fallen in love with outreach. I'm the one that runs the Facebook pages for the Mars rovers and for Phoenix. And now we've got Twittering astronauts. And I think that's a really good way to reach out to the younger generation. Not only have I been able to really inspire kids about NASA, speaking to them through Facebook, but also the older people that are on Facebook and Twitter. And the younger kids, their parents let them onto Facebook to chat with the spacecraft. So I just wanted to make sure that there would be good outreach for the future.
Thank you very much for your comment. Those were all very good comments, and we appreciate them. We will now proceed to the deliberation portion of the morning session, or this. We will now proceed to the deliberation portion of the morning session, or of the session. In the way of background for those who are joined us late, at the sessions last week, we began to put together individual pieces of the options that we might propose. Those pieces were studied in some depth by the various subpanels that we formed from our committee. Needless to say, when you put those together independently and you have so many different interrelationships, it takes a certain amount of integration. And we appointed an ad hoc set of our membership to do some preparatory work for this morning's meeting and for the meeting, the next meeting, to try to narrow down the possible set of options. And as I mentioned earlier, according to Professor Crowley, we have over 3,000 possible combinations based on the various separate cases we've looked at. And we don't propose to go through them one by one this morning, but we do plan to go through an abbreviated list. There will be other derivatives that we undoubtedly will want to discuss in our report, but we do need to narrow down to a few or a more manageable list, and that's our task before us right now. Ed, you've done the heavy lifting on this, so would you mind perhaps bringing us up to date with the preparatory work that was done?
Sure. Thank you, Norm, and I apologize for coming in a little late. As both the panel and the public can imagine, we're covering ground very fast here. But you can rest assured that I was keeping abreast of it because I was following the Twitter on Astrodude, which has a remarkably comprehensive track of the discussions. I have a minute. One more. So as Norm just said, an ad hoc group which essentially consists of the 3 or 4 of us who are leaders of the sub-teams met since our last public meeting in order to do additional fact-finding and prepare options for discussion by the committee today. So the outline of the remarks that I have prepared are first to review and discuss the potential decisions on human exploration. Secondly, to deliberate on these integrated options that we will carry forward and agree as a committee to a process going forward from today until our next public meeting next week. I should just remind you, both in the committee and in the listening public, that we did have an extensive set of discussions last week at our 3 public meetings. On Monday, Sally Ride's group on shuttle and ISS reported a series of options they brought to the committee for consideration.
That was Tuesday.
I'm sorry, Tuesday. And it was Houston.
And in what city was that?
On Wednesday, both Bo and Les Lyles presented the deliberations of their subgroups for consideration. And on Thursday, the Beyond Leo group presented its deliberation, and some larger scale recommendations, which were alluded to by several of the speakers, including the high-level assertion that the ultimate goal is to become a spacefaring civilization, and a discussion of why we go to space and derive from that, as well as pertinent policy documents of the federal government, the valuation criteria that will be applied to these options prior to our presentation to them, to the Executive Office of the President. So in order to sort of frame the space in which we're working, we try to state these as decisions which should be made. I've learned that when you speak with decision makers, they like you to have framed the questions you ask them as decisions. So this represents a compaction and narrowing down of the individual recommendations that were made essentially by the 4 subgroups over the course of last week. And I'll take us through them quickly. But it's important to understand, because when you see the integrated options, they are, of course, combinations of these individual decisions. The first is what is the phase-out plan of the shuttle? It is currently a matter of national policy that the shuttle will be retired. And the 2 principal choices that we laid out here as summary and simplification of the ones that Sally presented last Tuesday in Houston, are basically the current policy, which is to fly out the remaining flights safely. We estimate that will probably run into calendar year 11. This is currently policy, but the FY11 funding is not part of the current president's budget. Or alternatively, to extend the shuttle at 1 or 2 flights per year through about 2015, which, as Sally pointed out last week, only makes sense as part of an integrated option, which is combined with extending the ISS, having a shuttle-derived vehicle, a true shuttle-derived vehicle, so that there would be commonality of the infrastructure, and a emphasis on a commercial crew delivery capability to replace the shuttle. That's the first decision, 2 choices. What's the future of the ISS? Pretty simply summarized as end U.S. participation at the end of 2015, what has been the assumption in previous budgets, or to continue U.S. participation through at least 2020, and then there's 2 slight variants at a sort of nominal capability, or at what Sally called an enhanced capability. One decision, 2 options there. Then we move to the questions of reaching low Earth orbit. These are meant to be ranges so that we can sort of think of different possible vehicles within it. The 25-ton and below is meant to represent the existing ELVs as well as other commercially derived vehicles. The 75-ton range roughly represents directly shuttle-derived side-mount inlined vehicles of that class, and the 125-ton range is meant to represent the Ares 5 or variants of it. The 75-ton class could also include super heavy variants of the ELVs. The next question is, in fact, do we build this launch capability off of the NASA and shuttle heritage, things like the Apollo, the tanks, the solid rocket boosters, which are derived from shuttle hardware, the J2X, that family, which is, of course, the current program of record? Or should we consider, as a reasonable alternative, the EELV defense, national security space derived set of launch vehicles? Next decision is, how should crew be carried to LEO and to ISS in particular? And really here, at a policy level, there are 3 choices. One is continue the commitment to a government created and provided service. That's in the current program of record, Ares 1 and Orion. The second alternative is to, at this point, commit solely to commercial and international access. That is to say, to not have NASA develop an independent, federally funded launch system to LEO specifically for the ISS. And the third is sort of an option halfway in between, which is to encourage and rely on commercial and international providers for this humans to LEO service, but to maintain an option, or you can think of it as sort of as insurance or a backup, of having an alternative U.S. capability should it turn out that for either international reasons or domestic economic reasons, the commercials or internationals are not able to provide that service in the long run. You can think of this as a real option that it would be exercised within this choice. Next, what should be the plan for in-space depoting and refueling? We have, as a committee, discussed this, and particularly in the Beyond LEO group, quite extensively. We're quite interested in this, either as an enabler or an enhancer of future capabilities. If I were trying to sell this in the Senate this morning, instead of cash for your clunker, I'd call this cash for your rocket. This is creating the opportunity that commercial providers of launch services, in addition to a potential market for cargo to the ISS and potentially crew to the ISS, would additionally be able to provide fuel for purchase by NASA on orbit, turnkey operation, or something like that. The last 2 decisions, there are 8 in total, that make up this set of decisions that we have to sort through is what's the first destination for exploration beyond LEO? Should it be moon with surface exploration? Should it be deep space, that is visiting libration points, near-Earth objects, and planetary flybys, but with no immediate surface exploration? That is, you would develop in-space capability first and then move to planetary surface exploration. And thirdly, to do Mars first with surface exploration. So moon, Mars, or the deep space ocean. And finally, what's the role for commercial entities in exploration? To stimulate by choice of the architecture, options which encourage greater commercial involvement by providing on-ramps for example, cargo fuel, crew to LEO, and even beyond LEO systems, for example, like the EADS proposed, or at least the topic which was discussed by the presenter from EADS of having commercially provided modules which might provide both Delta V and cargo capacity beyond LEO, or essentially the current strategy. And Norm, in the process of our deliberation and preparation of the options here, you notice we slimmed it down to 864.
You're doing well.
So all we have to do is get to 3 by next week. That's not a joke.
Ed, can I interrupt just for a second? On number 7, the last bit, Mars first with surface exploration, last week you had mentioned possible touch and go on the moon. Does that still part of that?
That's sort of, Leroy, at this level, that's sort of a variant. And in fact, Bob Zubrin discussed another variant, which is sort of a touch and go on an asteroid or a near-Earth object on the way to the moon, way to Mars, I'm sorry. And, you know, amongst friends, I think you can sort of put those in and take them out of the Mars architecture without it being sort of a policy-level decision.
Right, and my cut on that was not so much for going there as much as to test your hardware and operations.
That's right. In all of those cases, and I think Bob would probably say the same thing, is that you really build the hardware to go to Mars, and as some combination of early capability demonstration / test flight, you would do some other things with it.
Ed, if we're having questions of clarification, just
I think it's probably a good point, Norm, to stop and discuss this much formulation. So,
just on the first question, flying out the shuttle, I thought there was an option in which there was, in addition to flying out the existing manifest, there would be one more flight taking advantage of the existing external tank.
That's well remembered, Professor. And in fact, in the attempt to sort of simplify and slim down, we put that in a note that's associated with basically flying out the remainder. We didn't think that at the sort of policy level, keeping an independent option of one more flight was a big enough difference that we wanted it. So yes, in the fly out the remainder, there's a maybe fly one more flight. For the purposes of the clarification, as Sally pointed out, her subgroup investigated flying a few more shuttle flights, and it turns out that there's a break point at 1, and exactly 1, because there is one more external tank that exists. So without having to restart the external tank assembly line, you could probably fly one more flight, and then there's sort of a big restart cost.
I don't think this is going to grow the space so much as it's something we have to keep in mind when we're looking at these destinations. But these have been made sort of as different as possible from each other so that we can think about them more easily. But then when you get down one layer deeper into it, it really, some of them start to look an awful lot like each other. It's just a question of in which order you do things.
That's right.
So people should not look at this and say, oh, deep space means we're never going to land on the moon. No, it just means that you're going to go other places, and then you develop the lander later.
That's right.
And moon with surface exploration doesn't mean, oh my God, we're never going to do propellant production there. It just means, well, before you get to the point where you're doing propellant production, we're going to land a few times. So just don't get. We have to call them something.
That's right. And I think another way to say it, Jeff, we're in complete agreement, is that if you did a 30-year view of how we would explore space, there would not be very much difference at all in these variants. I mean, there's I was going to say general agreement. There are some some reasonable disagreements about whether you should go to the moon on the way to Mars or you should go directly to Mars. I think there's general agreement, and certainly the position of our committee, that we should eventually go to Mars. There are certain capabilities that are required to operate in the Earth-Mars part of the inner solar system, which include launch vehicles to get off the surface, ways to inject large amounts of mass away from the Earth, habitats en route if the voyage is more than 3 or 5 days, ways to descend to planetary surfaces, ways to encounter non-planetary objects, ways to rove around on planetary surfaces, habitats on surfaces. And in really what these distinguish is which are we going to deal off the top of the deck first? And how do we try to do that within the guidance that the President has given us to respect the budget guidance?
Yeah, Ed, it doesn't represent a different option, of course, but I think one of the key things we discussed in our deliberations last week was to make international cooperation, enhance international cooperation, and underlay our foundation to all of these different scenarios. That's a sort of a bottom line recommendation that would apply to any one of the different scenarios we noted here, not just the one that mentions international.
Yeah, and that's actually in a chart a few down less, but it's well taken here. That it is certainly, I would say, characterize it as a strong sentiment of our committee that is the case. And in fact, when we get to the costing proposal, you're going to see a specific manifestation of that we are going to cost 2 ways so that we can sort of account for the possibility of significant international collaboration and contribution.
Ed? Yeah. On this subject, I'm not sure we have a uniformity of opinions in our committee, but I feel that lunar mission could be another forum for learning how to do international cooperation if we envision that ultimately we will go to Mars as an international venture. Because apart from doing technical things on Moon that will assist you in planning a Martian mission, there is another element that has to do with blending cultures, technical cultures, blending countries that fund things differently, that negotiate between technical people and people who lead their countries differently than we do in America. And I feel like there is an element of going to Moon which involves practicing this international cooperation, because it's a much simpler mission than going to Mars. I would suggest it would be very difficult to get, a dozen countries lined up and executing a Martian mission without practicing that process first by going to the Moon together, which is a much simpler mission and much less costly. So there is another little element that puts a different spin on why should we go to the Moon as an international cooperative effort and not attempt it for the first time on this very complex, very expensive mission attempting to go to Mars.
And I would say to not either agree or disagree with you, but to point out that one of the points that Sally made based on interactions with the existing international partners in the space station is that they have much of the same view about one of the important roles of the continued or extended utilization of the space station, that it then becomes more of a proving ground for a more multilateral international approach, which then might continue to the next destination, whichever it is. I don't know, Leroy, if you want to make any comment on that, or maybe Sally might want to from cyberspace there.
Yeah, I was thinking along the same lines. Certainly the International Space Station, as we discussed last week, has proved out we've evolved into a very good international framework. And one of the points that we made in Sally's subgroup was that the ISS can and should be used as kind of the training ground to how we would do exploration. But Bo's point is well taken. Going to the Moon is another jump above what we're doing on ISS currently, and especially in the context of putting international partners in the critical path, right in there in the critical path, possibly departure stages, landers, things like that. And so that would be even a step above what we're doing in ISS now. So Bo's comments are well taken.
And it's worth mentioning, as our European colleagues pointed out today, that the true internationalization of the International Space Station is really just happening in this year. I mean, the arrival of the Japanese and ESA modules, the availability of 6 crew, and so forth is really, it's been an international program on paper for a long time, and it's certainly a lot of hard work and development. But in terms of operations, this is really, we've really turned the corner in the last 12 to 18 months.
Ed, if I could add just a comment.
Please.
Yeah, I think, Leroy, thank you for that, and I completely agree with what you and Ed have said, and I'd only note that Bert's point is a good one, and the same could probably be said about the deep space option. That is certainly simpler than initially going straight to Mars, and that there are also a lot of opportunities with that option to incorporate a full international partnership to expand from the ISS and develop that operational capability further.
Thanks, Sally. Okay.
Ed, if I could just make one comment on number 4, just to again clarify some of the discussions that we've been having. It's great that it's framed as a question. In that case, it might be a yes and yes. And so some of the options, in fact, are not mutually exclusive. And if we look at the evaluation criteria, things that we would value in terms of industrial base and workforce and all those things, we'll find that I think there's some intersections there. So, again, I would say that, some of the options that we've looked at have benefit to the nation. We talk about, pursuing our leadership in space, that suggests that it's not an either or. It may be that there are things that we do on both sides of that.
Yes, excellent point. Many, but not all of these choices are mutually exclusive. But they shouldn't necessarily be taken strictly as such. But of course, as Norm would point out, that would then increase the number of total possible options. If you can say A or B or A and B, like all those tests we hate. Any other comments before we move on to the integrated options? So to warm you up to the way that we're going to present the integrated options, we're going to present on this chart, and I apologize for this being a little eye chart, but I'll try my best to walk you through it. You see down the left-hand column 4 options which are going to be at least considered, if not included in our final report, just for reference. These are not options for considering going forward, but they're sort of a historical perspective of the past and present evolution of the program. So you read across the top, and the first column after the main option column, that is to say the second from the left, is the intent with respect to the budget, which is the current FY10 budget covering the period from 2010 to 2020. The next column is what the decision or recommendation for the shuttle retirement is. The next one is ISF's effective life, that is to say U.S. involvement. The next one is crew to LEO. The next one is heavy lift option. The next one is there a refueling option? Then there's the first beyond LEO destination and the strategy for commercial engagement. And the top line will be a representation by us of the program of record. We think it's important and fair to lay out the program of record as it is NASA's current plan, because of course continuing it would be an option that the national government could exercise. So in terms of these questions, the program of record exceeds significantly the FY10 budget guidance. It retires the shuttle in 10. There is no funding in the budget for ISS life after 15. It has the Ares 1 and the Ares 5 for crew and heavy lift. It does not explicitly consider a refueling option. It goes to a lunar sortie and probably outpost mode, although I must be fair and say that the specific mode of surface exploration has not been decided upon by the program, but I've used it here as sort of a shorthand to represent an outpost, and that there is a COTS cargo component. The next line down does not vary in any way from the program of record, except the committee, with support from NASA and the Aerospace Corporation, that is to say PA&E, the independent group working with us from NASA, and the Aerospace Corporation, will represent our assessment of how the program of record would likely have played out, just so that the political decision makers will get some sense for our view of the likely evolution of this well-documented program were it to have been allowed to evolve. The program, and that includes, you'll notice, extending the shuttle to 11, which we think is the likely thing to happen. The next line, called increased confidence, is actually an option proposed by the program of the Constellation program, which expresses how they would prefer to deploy additional resources to increase schedule confidence and decrease the risk in their program. And just for historical purposes, we will put on this array the best reconstruction of the original 2005 plan, if nothing else, to point out in the first column, or actually the second column, the budget column, that the program was actually designed to the then budget guidance, which was significantly higher than the current budget, than last year's budget guidance, which is significantly higher than this year's budget guidance. So we want the White House to understand that as they move the target from what NASA was looking at last year to what's in the current guidance, this is the second significant reduction that the program has seen in its budget, and that the program was in fact designed for a significantly larger budget than last year's budget. So a way to show this is to represent something like the original plan, that when the design decisions were made in, let's call it the 2006 timeframe, the budget that the decisions were made to. So for example, as the former Administrator Griffin would remind us, there was little gap in that program. That program had the first IOC of the Ares 1 in 2012, but as a result of various things, including the reduction of budget, that date has now slipped significantly out to later than 2012.
Ed, just as a nit here, how would it be if we put that last one first, so that we can start out with, this is the way the program began, this is where we are today, according to the record, this is where we think we are today.
Right. I think that's probably a good presentation choice.
And then before you move on, a clarifying question. Original 2005 plan, you're referring essentially to ESAS.
Yes, it's the ESAS era plan. And I think we'd actually probably, Jeff, capture the next budget, the budget that had caught up with the ESAS plan or something. We have to do a little bit of work on that, but that's the intent. And of course, we called them in that era the crew launch vehicle and the cargo launch vehicle, which have evolved into what we now call Ares 1 and Ares 5, but not without some substantial changes. Well, the next chart is what General Schwarzkopf would have called the mother of all briefing charts. And it lays out in one chart the about 7, although if you read carefully, you'll notice there are significant variants even within one of these lines. But the about 7 options that our subgroup is proposing that the full committee deliberate on and consider taking forward by a process which I'll describe. Now, in order to sort of try and give you a little bit of a guided tour of this chart before I go into detail, and it's basically the whole rest of the briefing is on this chart, let me show you intent. The top 3 rows, called baseline derived from program of record, ISS focused, and dash out of LEO, are the ones where we are trying to be true to the guidance proposed by the White House to us in our statement of task, to come back with options that have a credible chance of fitting within the budgetary guidance of the President's budget. We're not sure yet. We haven't sharpened up the pencil and we haven't done the costing exercises. But these three are the ones that we intend to fit within that within the budget guidance. The four lower ones, starting with used shuttle systems, deep space, lunar, global, and Mars first, are the ones where we have decided that we will not constrain ourselves to the President's budget guidance and see how these come out. The other way to think of this, so let me begin, and I'll just sort of walk you. This is basically the same chart over and over again, but with a different row highlighted, just so you can see the one that I'm talking about. So the first option that we are currently proposing to examine in detail is called the baseline, which is derived from the program of record. It's actually developed by the program of record. And what it would do is basically take the content of the current program and treat schedule as the independent variable and move the milestones to future years, as we say, to the right on the chart, in order to accommodate the budget, recognizing that that increases the cost, ultimately, of reaching any of those milestones. But it does stay within the budgetary caps in any given year. So it's more or less exactly the program of record as described here. That is to say, we give the shuttle the extra year we think it'll take. We withdraw U.S. active participation, federal government participation in the space station in 2015. We rely on international partners transitioning to Ares 1 to provide crew to LEO. We develop the Atlas V heavy lifter. There's no refueling option. We go to the moon with sorties and an outpost, and we use COTS cargo, and we see how that plays out within the budget constraints. There are two other strategies at a high level that you could imagine using to try and fit within the constraints. And the thinking here is that it's either or, but not both. Either, as this one suggests, you put your emphasis on developing and continuing to exploit the International Space Station, and do that robustly, and allow the rest of the program to explore beyond LEO, to basically slip even more to the right, even farther out into the future. The other option is to wrap up the U.S. government participation in the space station as quickly as possible and leave low Earth orbit as soon thereafter as the budget allows. That these are sort of the limiting cases. Focus on the ISS or move past the ISS to the stated federal policy of exploring the moon, Mars, and beyond. So the reflection of the current one that's highlighted, ISS focused, is basically we tried to stay within the federal budget as prescribed by the guidance. We retire the shuttle in 11, but we extend the space station until at least 2020, and we bet on all the horses to close the gap from above. That is to say, we have to, in the short term, rely on the international partners, that we develop the Ares 1, because it will have many years to go to the space station, we hope, and that we bet on the commercial providers of launch to LEO. That at the pace that the budget allows, we continue to develop the heavy lift Ares 5 with no refueling and its planned eventual program to go to the moon, and that we not only support a commercial cargo, but a commercial crew capability by providing COTS-like or Space Act-like mechanisms to acquire those services. So this would be robust utilization of the space station, but allowing exploration to move off into the greater distant future. It's a limiting case.
Ed, before you leave that comment, the questions you had previously, there were two cases of how active one should be aboard the ISS during this additional 5 years. And it would seem to me that if one does do this, the second option on this page, that one should then make the additional investment to be sure you get something useful out of ISS.
That would be the consistent.
Right.
Right.
And so we could drop that other one and put, in other words, this one is the added additional money.
That's right.
Very
This is
good.
the sort of full-up ISS utilization option.
Right.
That's exactly right. The other bookend is within the prescribed money and trying to fit within the guidance. The other option is put the emphasis on exploration beyond LEO. So the dash out of LEO or explore beyond LEO as fast as possible within the President's budget would retire the shuttle in 11 and terminate U.S. federal commitment to the space station in 15, and therefore it makes no sense to us to do anything other than to rely on the international partners to provide that crew access. And it would use a variant proposed by the program in their briefings to us and that I discussed last week in Cocoa Beach, of actually creating what is referred to as the dual launch Ares 5 strategy, in which there, instead of being a 1.5 launch, an Ares 5 and an Ares 1, that there are two slightly simplified Ares 5s used to launch all the things you need to go to the moon in 2 launches, rather than the so-called 1.5 launch strategy. This would cause the federal government to skip over the Ares 1 development and emphasize as soon as possible, as soon as practical within contractual limitations, the development of the Ares 5. And what it would do is then, in order to save budget and defer the cost of the lunar landing systems and lunar surface systems, it would delay those even further, and it would develop some in-space habitation and propulsive capability, perhaps in coordination with international partners, which would allow us to visit lunar orbit, the Lagrange points, the points of special interest in the edge of the Earth's sphere of influence, near-Earth orbits, and potentially, although even in this option it would be somewhat out, potentially planetary flybys, gaining capability of operating in deep space. But the emphasis here is that that would be done within the President's budget, within the budget guidelines. So those are the 3 options, which are basically, simply put, stretch out the current program to fit the budget, emphasize the use of the space station, but delay even further the exploration beyond LEO, or terminate on the current schedule, that is, say, the schedule that has been assumed in the past, the use of the space station, and put as many resources as possible that the budget allows in going beyond LEO.
And
Norma, you want to, maybe that's a good stopping point if we want to discuss those 3.
I'm happy.
Chris-
Anybody else want to?
Chris had a point.
Okay,
I think
we got a
there's
couple
several.
folks. I saw Chris and then Jeff and then Les.
With respect to what you call dash out of LEO, since that's, you're shedding everything you can to get beyond low Earth orbit as fast as possible, what's an estimated date for when we get a first mission beyond LEO?
Really good question. So maybe this is a good point to sort of answer to answer that by flipping ahead a few charts, because it's probably the question on everyone's mind. And you'll notice that other than the dates which are set by decision, like when you retire the shuttle and when you no longer have federal government involvement in the space station, there are no dates on here. So if we go down about, yeah, I forgot all those words. One more. So this is the proposed method of answering that question, Chris, which is that we have now defined by the work of our various subgroups approximately the content of each of these options. We have to do a little bit more detailed definition. But we know about the capabilities, as Jeff just said, about the sequence in which the capabilities come online. And what we're going to propose, or are proposing as a way forward, is basically these 3 bullets. First, that we develop a budget and schedule that matches this content and sequence of content and the assumptions and the budgetary assumptions for each of the integrated options in two ways for most of them. One of them is constrained to the FY10 budget guidance with schedule as the free variable. We just say we will follow the president's budget guidance and see where the milestones occur. In other words, Chris, the short answer to your question is I don't know yet, right? Because this analysis is still ahead of us. But the other thing we're going to do is to cost these not constrained by the president's budget for two reasons. One is that in some of them we don't intend to actually try to fit within the president's budget. We intend to see what a robust program would be at a level higher than the guidance in order to potentially make a case for that. But the other is, as was pointed out to us in a recent telecon by the budget folks, is that if you actually expect some commercial or international contribution, what you should really do is price the programs above the budget line and then reason whether the amount above the budget line could legitimately be contributed by other partners. Because if you put it below the budget line, it would have that multiplying effect of moving all the milestones out. So we intend to look at it both ways, constrained by the budget and not constrained by the budget, because it may be that additional international or commercial resources come to play, basically causing some of the cost to be relieved from the federal budget and absorbed by other partners. But I wish I had the real answer to your question.
Jeff?
Got a couple here, and they're all budget related, so they're all things we don't know yet. We've discussed informally that, you know, there's outside the budget and then there's way outside the budget. And, you know, I think there's a lot of interesting options that are maybe beyond the current budget, but not by an amount that might be out of reach. And it's hard to tell from this kind of what your subgroup's intent is going forward.
I'll defer to our chairman.
Well, my reaction is there's no sense proposing things that are dead on arrival. And if there are plausible, doable, useful programs that are in your first category, we ought to do it. If there aren't, then we're in the second category.
Okay. Now, that was not actually my original. I'll be clear.
Or said another way, you know, I think that by doing these and the variants that are represented, we will get a little bit of a value curve. We'll get a cost and benefit, a sense of the costs and the benefit of additional investment by the government, and we'll have some sense of that trade.
The point I wanted to raise that's deeper than that is that chart makes an assertion, and the assertion is that none of the next 5 options are within or close to the budget. And I don't think that's correct. I think there are variants of some of those that are within a reachable distance of the budget guidance.
That's a fair comment. That when I flip back, I'll point that the greater than might actually be greater than or about equal to. Right.
Let's see, Les next, and then Bo.
Yeah, just for completeness, and because we've discussed this, obviously, and I know you're going to talk about it in the next chart. Can I suggest one mod to your matrix here? It's an excellent one. But after the commercial engagement column, we have a column that says international participation. We put importance to that. I have a feeling this charter is going to have life of its own in the future, and because it is something that we think is a valued, very, very valued consideration, that we capture that.
Yeah, an excellent point, and we were just trying to. I think we all understand the importance of that, and we were sort of thinking of that as a wrapper. And there is a subtlety, which is that at least in principle, the choices that are made in corresponding to these decisions are under the control of the federal government. When we retire things, how much we fund things, which capabilities we build first, and there's a subtle but important distinction of not wanting to sound too prescriptive about the role of internationals in these various ventures. So That's the
understand-
balance we were trying to
understand.
strike.
From a policy standpoint, this is also somewhat in control of the federal government also. That's
Well,
why we
the
don't want to.
policy about engaging internationals, absolutely. Yeah, right.
Bo.
Yeah. In this upcoming costing exercise, and I made a point of it previously in Huntsville, and I'd like to make it here again, it's absolutely essential that we make sure that whenever we recommend, or not recommend, but lay out a program that is going to replace, by someone's choice, probably salary grade higher than ours, to make a choice over the program of record that we clearly account for all the costs that are associated with the changeover. And some of them are not easy to see. Some of them, what I'm trying to avoid is a bunch of hidden gotchas that NASA is going to be struggling later after somebody sort of took a, friendly view of a paper program, and we didn't account for all the cost items that really will result from changes. Changes, changes some people love, some people hate, they always happen, and they bring along with them surprises. And it's our job, as well as we can. We had a little time to do it. We had help from our aerospace friends and consultants, and I think it's very important that we don't send the country on some chase of things that has a bunch of what I call affectionately hidden gotchas. It's very important, and
I think in our public meetings in particular, on our tour last week, some might call it a road trip, that we heard many pleas from both the management and workforce for continuity that we would have to consider. In specific response, Bo, to your comment, the excellent report by the Aerospace Corporation on the relative assessment of the ELV as a crew launch capability, which I believe was issued as a public document this week, when they costed out the transition costs there, they actually identified a set of things that could happen within 6 months of a decision, a set of things that could identify what could happen within 12 months, and a set of things that it would take 18 months within such a decision to occur based on experience in historical records, historical evidence of previous major contract transitions that have occurred. And you're absolutely right. We have to factor that in. And I think with the help of aerospace in this process going forward, we'll make sure that's represented.
It's my turn here. Sally pointed out to us that the program of record does not include money to deorbit the ISS, and at least for the 2015, we ought to make a mental note to include that.
That's an excellent point. I think she pointed out that it doesn't include enough money to deorbit the ISS, but
that may be.
Yeah, I can actually clarify that because we've gotten, yesterday afternoon, late-breaking news, we got an independent assessment from Aerospace, and they identified some significant costs that are not presently included in the budget that would be required if ISS were to be deorbited. And we'll make those available. I think we just spread those around last night, distributed them last night, and that will definitely be part of the costing for those initiatives.
And I guess that should be included in both 2015 and the 2020 case.
Right. One of the benefits of looking at the 2010 to 2020 window is it moves that out, which is, of course, a false economy. But other questions on the first three? If not, I'll go back to let's go spool up about 6 slides. One more. Oh, that's the right one. Another option, which starts, the thread for this one starts with an observation that Sally's group made, which is that it may make sense to, if you were to decide that an appropriate way to do heavy lift was some vehicle directly derived from the shuttle, or one might say more directly derived from than the Ares 5. And I've called that a class here under the heavy lift category, directly shuttle derived, and that's a placeholder for side mount inline options and things that use SSMEs and so forth. That if you were to choose that, then it would make sense to consider extending the life of the shuttle beyond 11 by a few years. We've used as a placeholder here 2015, so that you could both close the gap and reach synergies between the operation of the eventual heavy lifter and the operation of the shuttle. So this is one in which, and here I'll take Jeff's friendly amendment, this could be greater than or roughly equal to the President's budget. We haven't done the costing yet, but we would allow it to drift more than the President's budget if it called for that. And then the crew to LEO would be provided in the interim, and this presumably would be a relatively low rate. I think Sally's report said 1 to 2 launches a year. And I think, as I recall, Leroy, discussions with the shuttle operations people felt that they were comfortable from a safety perspective going that low.
Yes,
Right.
that's correct.
Yeah, so we've done that diligence. So that you would then use some combination of the shuttles and the IPs, the international partners, to reach the space station, and then eventually commercial providers of launch to human launch to LEO, crew to LEO would come on. This would only make sense if you did it in conjunction with a directly shuttle-derived vehicle, which really would only make sense also if you developed the capability to enhance the upper stage of a directly shuttle-derived vehicle with some sort of fuel transfer, tanker or depoting idea, so that, as Jeff discussed in his discussion of depoting last it was a Freudian slip, last week, that the important parameter for the design of missions beyond LEO is how much mass can be injected away from the Earth, not the size of the Earth departure stage, if you allow there to be refueling of the Earth departure stage on orbit. So there's actually many things that have to work together in order to make this option make sense, but if you made all these choices, then this integrated option does fit together and will be one that we recommend evaluating. The next one is, in fact, sort of an elaborated version of the dash out of LEO. It's one where you allow the shuttle to fly to 11 and, not or, and operate the space station until 20. And in that time, you would first use all the words aren't here, you would first use the international partners' Earth to LEO cruise transfer capability, and then you would strongly encourage a development of domestic commercial capability, which is over in the last column. And for these two, we've kept the idea that while the committee is strongly in favor of encouraging the development of domestic U.S. commercial crew capability to low Earth orbit, it's one more step to say, and we're ready to commit the nation to it. In view of all of the uncertainties that occur in the business community about the delivery of services which are funded by the companies and by investors, that we think that it's prudent in at least some of these options which rely on a commercial crew to bookkeep another option, the idea that there's some insurance that somehow in the U.S. launch capability there should be the ability to quickly reconstruct, if you will, the capability to launch U.S. crew to orbit on a U.S. launcher. So this is sort of rely on the commercials but have a little insurance policy as a strategy. Likewise, in this one, we could imagine, and we are still considering both NASA heritage, and that would include things like Ares 5, of course, but it might also widen that space up a little bit. NASA heritage, heavy launch vehicles, or what in the EELV family would be called super heavies, things like the Atlas V Phase 2 Heavy, which is a roughly 75 ton to low Earth orbit capability. And consistent with the deep space destination, it would go to lunar orbit, the Lagrange points, to near Earth objects, the asteroids which cross Earth, and conceivably within the foreseeable future to planetary flybys, and we would encourage commercial cargo and crew supply. The next one is Lunar Global. This is not too far from the current strategy for exploring the moon, but one that allows the budget to be relaxed. Again, 11 for the shuttle retirement and 20 for the space station termination or withdrawal. Same strategy for crew to low Earth orbit, same strategy for heavy lift, and the difference is really in the destination. And that you would go to the moon on a sortie and extended sortie stay, much like the mode in which you would first explore the surface of Mars. At least the reference missions, including Bob Zubrin's reference mission and the NASA reference missions, do not call for initially developing a base-like or outpost-like capability on Mars. It's more of a self-contained lander that arrives and goes to different sites on different opportunities and allows broader exploration of the planetary surface. So this is our moon variant, lunar variant, which more explicitly, both in the technology and in the subsystems and system concepts, would prepare us to take the next step to Mars, having spent some time on the moon. And the last one is actually very close to, conceptually, to both the one that Bob Zubrin presented this morning and to the the NASA Mars Design Reference Architecture 5.0, which is an option in which we do, in fact, go directly to Mars with the friendly amendment of maybe you take the Mars hardware and go to a near-Earth object or do a test flight to the moon, but only for the purposes of validating and demonstrating the Mars hardware. So we would, in that, almost certainly need to extend the ISS using IPs and then commercials. And here we take all of the budget for all practical purposes other than some stimulation of the commercial launch to LEO business and the money to extend the ISS, and we put it on building systems for Mars, and we build them as quickly as possible in order to reach Mars as the next destination. So Norm, that's still many, but many fewer than 834 or whatever the number is. And I did try and get through it in a timely way.
You did a terrific job. Sounded like the same sessions I was in fact. I'm happy. Are there questions, comments, concerns?
Norm, I have a comment, if I may. You know, this is a pretty small subset of what we looked at, and I want you to know it wasn't easy to come up with a set. It was not easy. In fact, as we went through the process of trying to figure out what makes sense using our judgment, experience, and also the input from aerospace guys, I personally became more appreciative of the wisdom of the original Ares 1, Ares 5 configuration. And I think given enough money, these guys could have finished this job and served this nation well. But they don't have enough money. Their budget has been cut over the years, and I've seen some data recently that is sort of shows just by how much. So I'm telling you, this is not, these alternatives are not a reflection on the guys who created the original architecture and were trying to serve our country via that architecture.
Probably also should footnote that we discussed still adding some boxes or something where there are interesting derivatives not worthy of this list, but that should be call to people's attention. Chris, did you have something you wanted to add?
I have a question regarding the U shuttle system scenario. The first Beyond Leo destination is listed as Lunar Sortie Outpost. Could you just say a bit about why going to the shuttle-derived vehicle would drive you to that being the first destination? Why couldn't one have a more deep space type set of options there?
Ed, could I make a comment also?
Sure.
Chris, I actually think that's a really good question and a really good point. And I would suspect that after we've done the costing of these and seen what happens with budget and schedule, that we may discover, and we just haven't had time to discover this yet, that in putting together some of these options, we may have combined things like the Close the Gap with perhaps not the best exploration alternative. And I'm not in a position to say right now whether we have. Ed certainly has a better perspective on the Beyond Leo destinations. But I've had the same observation actually in a couple of them, that as we get smarter over the next day or two or three or four, it may become obvious that a little bit of mix and match produces better integrated scenarios. But this struck me as a very good place to start, since we have to start somewhere with a finite set of options that need to be costed.
I would take both of those as friendly amendments. I think that the committee should reserve the right to sort of spin these tumblers several different ways as we work our way through it in the next week or two.
Jeff?
On the deep space and the lunar global lines, again, trying really hard to find some way to get these sort of kind of vaguely like the budget. I want to talk a little more about what we have in mind, or what I want us to have something in mind about what is this U.S. backup to international partners and commercial crew to LEO strategy. And in particular, I see a big bifurcation in that there's a set of more expensive options where what you're talking about is coming up with a crew-compliant booster that's big enough to loft your exploration capsule to ISS. And there's another much less expensive sort of options where what you do is you still let the commercials develop sort of a crew taxi with maybe enhanced U.S. government support, and the U.S. government provides a backup booster in case their boosters don't go. And I'm not sure if this is both of those or which of those.
I think it's all of those. Okay. In fact, I think there's three classes of things. You mentioned two of them. You mentioned the U.S. government providing a more robust option by providing a launch vehicle, under the argument that it might be easier for the commercials to develop a capsule than within a fixed amount of time. It might be easier for the commercials to produce a reliable capsule than a launch vehicle with the demonstrated reliability that you would expect it to have before you put a human on board. So that's the robustify the commercial launch capability. The second class of options you also mentioned, which are whichever route that you go through for the heavy, you could have a variant of the heavy that was light, right? So if you did the Ares 5 as the heavy, there are variants of the Ares 5 that could carry crew to low Earth orbit. If you did a Delta 5 Phase 2 heavy, you could use the Delta 2 Phase 5 medium as the backup plan for crew to orbit. So there's a class where you make simplification of the variant of the heavy, and then the third class is if, for example, you choose to skip over the Ares 1 and go directly to the Ares 5, that you would keep alive enough capability of in the Ares 1 because of the commonality between the 1 and the 5, so that in a relatively short order you could go back and finish the 1. So there are several different ways to, depending on exactly the launch vehicles that get picked, to think about how you would do that.
In that case, I'll just note this is a deceptively simple chart, because there's really a lot more options on here than it looks like.
Are there any? Bo?
Hey, one thing, I sort of react a little bit like my younger colleague here on this U.S. backup. It sort of implies that we don't think that the guy working in a private industry is as reliable or as conscientious to design a system that will launch people to space. I don't agree with this, by the way. But I think it's very important that when NASA competes for these commercial capabilities, that they structure their procurement in such a way that our best and most reliable contractors bid on it, and NASA selects not only the newcomers. I think it's very important to stimulate commercial industry, open the door so that so the newcomers can come and play in this game. But it's also important, especially when it comes to launching humans to space, that the people, companies with the best skills and the best capabilities are also allowed to bid, and NASA select at least one of them. And I think that's how you assure that we have a safe access to station and LEO, and without necessarily having a U.S. government backup.
Well, if I can respond to that, and this will demonstrate to the public that we really are deliberating, I don't agree with you. But I actually don't agree with you in a different part of the argument, Bo. I don't have any doubt that the commercial community could provide these capabilities technically, right? But the first word in commercial launch is commercial. And as somebody who sits on boards of both private companies and public companies and has some insight into the fiduciary responsibility of board members, I know that every quarter and certainly every year, boards of directors are legally obliged to make decisions about the investments of corporate assets to optimize the internal rate of return for the shareholders. And unless the federal government structures the commercial acquisition in such a way so that there are reasonable assurances that there in fact will be markets for these things and there will be, essentially there will be a market, then it introduces a great deal of risk into those business decisions, which is my concern, not the technical capabilities of the organizations to deliver. And there are, we know, various mechanisms under the Space Act and mechanisms used by other government agencies in times of when it is expeditious on behalf of the nation to not directly apply the federal acquisition regulations. Les would know much more about this, that there are other mechanisms by which assurances can be given to corporations to provide services on their investment. And you might want to comment on that, Les.
No, you hit it right on the head. I think that's exactly the other consideration that goes into that process.
All I want to add to that is, at a time when we're trying to present national policymakers with ways to do more with less, we can present them with recommendations to put those tools in the toolbox. And commercial is a shorthand. It's not just about who you buy from. It's probably much more importantly with how you buy. You can buy commercial things from quite large companies, but you have to do it that way.
And I think what this flags up, Norm, is that in this discussion of commercial, there's actually quite a bit to be said about business practice by the government and how these acquisitions are structured.
Let's see, as a peacekeeper here, let me propose a solution, and that would be that we have a separate box that we take out of these boxes either the U.S. backup or the commercial, and in a separate box, say if you want to do it, I don't know which you make the baseline, but let's say you make the baseline having the backup. Another box would say if you don't want the backup, you could save X dollars and take risk for it.
Okay. I think that was intended to be in there, Norm, and it's just in the way it came out.
I think that solves Jeff's concern.
Okay. There's one specific axis where that doesn't do it, and where we can't, I don't think, box the problem. And that specific axis is the choice of a NASA heritage or a more commercial DoD heritage set of vehicles going forward. And the reason is that ripples through so many other aspects of the program that even though the capabilities might be similar, the stakeholders are all different. The budgets are all different. The workforce implications are all different. And I don't think that we can treat that as a box. I think those are actually distinguishable options for that reason.
Well, if that's true, then you've got this page about 11 options.
Well, it's not a perfect world, but
it's not a perfect world, but if you take 11 options to a senior decision maker in this country, you're liable to get any answer, I'm afraid.
well, I appreciate that. Maybe we can find some other ones to prune, but
So, Norm, there's just a few charts at the end here that I want to end with and get off the stage. I just wanted to remind us, this was less the note about international. There's an ongoing discussion about international, the role of robotics, technology development, and the role of NASA and its institutions that will, of course, be reflected in the report as well. But we're not explicitly, at least yet, embedded in the option choices. And we discussed many of these last week, and they reflect our statement of task from OSTP. So on the next chart, I think we've done this. We basically argued about whether it reasonably captures the report of the subgroups. Are they reasonable and consistent? Are they? Is there any evidence, new evidence that would cause us to add some? Are there any options that could be deleted? I'm afraid we didn't get very far towards the deleted end of the spectrum.
Well, let's. What I would suggest we do is go ahead and cost these out, determine the schedules of when you get where, and see if there's a simpler version that we can come up with how to present the results. I think all the options are very justifiable. It's just that I worry about trying to explain this, and so maybe there is a simpler way to show it. And if when we go through it there's some options we can put aside or deal with in a box or something, that's great.
So if we go to the last chart, that's the plan, which is that we, as I alluded to earlier, we'll cost these out with and without the constraint of the guidance budget guidance. And that we will also evaluate them based on the valuation criteria which we presented to and was approved by the committee at the meeting last Thursday, so that we understand that we're looking at these in terms of exploration, preparation, science, et cetera, and that we present these results next week for the deliberation of the committee.
Well, I think you've done a terrific job, and if we could come back next week with less than 834, that would be very good. Does anybody want to have a last word? Jeff wants to have a last word.
well, we may not be the last. I'm sorry, but we're not out of time yet. I think there may be a pruning option. You'll like deletion. I'm not sure that at the level of national policymaker decisions, dash out of LEO and the deep space option are so distinguishable that we have to track them separately. I mean, the only real difference between the two, considering that NASA Heritage is already, contains, depending on how much budget you want to spend, Ares 5 as a subset. The only real difference is, do we or don't we extend the space station? And I'm not sure, given our limited trade space, that we want to have another one of our primary options that doesn't extend the space station. And if we didn't have that, we could drop one option.
Well,
the difference is this, the budget, the dash out of LEO is in the budget.
Well, but again, some of the, as discussed earlier, some of the variants of the deep space option that are maybe stretched out more schedule or use less expensive launchers do become budget compliant or close to it. I'm trying here.
Yeah, you're right. The difference between the budgets available for exploration beyond LEO and those two options is on the range of $12 to $15 billion in the window, which out of a budget that would go to Constellation of about 70 is not a small change, but it may not be larger change than some of the other changes that are embedded. I get you. Maybe we'll think about that.
Chris.
So I'd like to float just one other topic here that we're not going to resolve today, but I think it ought to be on the table. This chart's titled Integrated Options for Consideration Going Forward. And if we think about the way it cuts through the Constellation program, it reconsiders the various options. Reconsider how we're going to get to low Earth orbit. Is it Ares 1 or not? We reconsider heavy lift. Is it Ares 5 or not, with various options. because we're considering destinations, we reconsider whether we're going to have the Altair lander or not, or at least whether we're going to have it sooner or later, or something else presumably. What isn't explicit on this table, and what one of our public speakers emphasized today, is what about the crew vehicle? There is, of course, if one goes with some of the commercial options for crew to low Earth orbit, one would have a different crew vehicle. But I don't see a kind of systematic discussion here of what, if anything, our thoughts are about the crew vehicle, and probably we need to formally discuss that at some point.
I think that's a really good point. One of our earlier versions had a column for the crew vehicle that at least addressed whether it was a 2 or a 4-person crew. That we probably ought to add a column back in for that as we do our work. Wanda?
I had a comment I wanted to make, again, generic, as we start to think about the report and how we formulate that. I think we heard, from many different cities that we've been in recently, the need to make sure that what we take forward, really is executable and doesn't have these little hidden surprises in them. So I think it's important that we capture our assumptions on some of these in the report in terms of what our intent was. Because as I look at, for example, the ISS-focused full-up ISS utilization, I'm not sure that I would be able to really say what we're assuming there in terms of the number of astronauts that we're thinking we would be able to transport in order to support that full utilization, in order to say that we really were getting a tremendous value out of that. And there, I think, are a couple of others here where, as I listen to all of us, we have different ideas about what's built into it. So I think it's really key that whatever options we come forward with, we somehow are able to communicate what the assumptions were behind it, and maybe why we thought it was important.
Good point.
At the risk of
Norma,
extending this,
I don't think I was advocating that we add another column to the table. I think I think that would be the wrong way to go. I just wanted to float the fact that we haven't, I think, as a committee, deliberated on this question in any detail of the crew vehicle.
well, maybe we should take a couple of minutes.
Jeff, I think you have something to say.
Well, I'm here's another Nixon goes to China moment. I've been as strong a critic of the size, particularly the size of the exploration vehicle that we're engaged in developing right now as anybody has. Were we possessed of a time machine, that would be one of many things we would like to reopen, but we're not. And so I simply can't see reopening major changes to the exploration capsule from an engineering and sort of project management perspective unless we look at options in which initial operating capability of the capsule starts getting out into the 2020 plus time frame, because it's going to take that long. If we really crater that program and start over, it's going to take that long, and if we try to do minor course corrections, it's going to take half that long for almost no benefit. So I just, much though I wish we were in a different universe, I would recommend that we not add that dimension to the trade space.
Were you thinking of a crew vehicle of less than 4?
I've thought of a lot of things, but they all look so different than what we have under development right now that the programmatic implications of trying to go there would not, in my opinion, lead us to a place that we would like.
The reason I ask that is apparently in reality we have a crew of 4 vehicle today, whether we like it or not.
Yes.
And to go much less than 4, I wonder if you start getting into workloads and psychological issues that get pretty tough.
Let me just say, if we had designed the system from the beginning for a maximum capability of 4, it would probably look quite different than it does right now.
Yeah, I don't know that, but it could be.
No, I think that I think Chris was right in raising this point, but my sense is that the reason it hasn't made it on the trade matrix explicitly is that there's a general consensus that's developed among the group that more or less Jeff just articulated, and that we should just make that explicit. That at this point in that program, barring some overwhelming reason to change it, it's at a programmatic point where it's unlikely that any small change or large change will do anything other than delay it extremely. And I think we heard from both the commercial provider and the program manager of it to that effect.
Any other points?
I have one sort of closing thought, Norm. Our first international speaker, Jean-Yves Le Gall, started by addressing us as a commission, and in his excellent but French accented English. I wasn't quite sure whether he said the August Commission or the Augustine Commission. So I would comment that we're certainly the Augustine Committee. I hope someday we'll be referred to as the August Committee, but we're certainly the August Committee.
I think we're
and we have to work to get this stuff closed out by the end of the month.
We're the Committee on the Future of Human Spaceflight in the U.S. Anybody else? Speak now or forever hold your peace.
Well, if that's a...
That's the criteria, both.
You know, if I may, Norm,
The audience is starving, you know, Bo.
Okay.
Go ahead.
Go ahead. Just final thought. You know, I hear it like once a week. Flying to space is hard. Well, flying to Leo is a little easier. Flying to Moon is going to be harder. Flying to Mars is going to be much harder. I mean, this is like a various level. NASA is good that we have handled this flying to Leo for a long time, you know, and we are, and you know, Mr. Zubrin said we are stuck at Leo. Well, you know, that's one way to look at it. And I feel like, you know, NASA has brilliant people. Get attention of these brilliant people on the harder tasks and think of buying the easiest task from industry. And I think if NASA does that, I think it would elevate, it would strengthen NASA. NASA would show off their skills in doing the hard stuff. And by the, you know, it's not simple, it's still hard. Going to Leo, I mean, God, I've been in this business for a long time. It's still hard. It's a little bit easier than going to Moon and Mars. So, and I think NASA, if they works on these hard tasks and introduce vigor into commercial industry, I think that process would elevate NASA in stature in America.
I'll add a thought to in that sort of vein, and that is I've refrained from referring at all to the study that was done 19 years ago, believe it or not, after the Challenger accident. But one of the things that was recommended there was to get on with building a heavy lift launch vehicle, because that's kind of the ground floor to everything. And I think one of the lessons that most of us have learned in our career is don't skimp on the heavy lift part of it. Let's have enough lift so we can have margins. And I think as we go through our recommendations here, that's one of the things that we want to have in mind. Now, if I haven't opened Pandora's box, anything else? Anybody? Okay. Let me just say that we have our work cut out for us. We will meet again next week. We have 26 days remaining before our deadline. Thank all of you. Thank our speakers, our public participants, and have a nice day.
Bob, good to see you.
Sir, great to see you again. How have you been anyway?